On a quiet night in the Utah desert, Earth was hit by a single particle carrying the kinetic energy of a fastball, packed into something smaller than an atom. It shouldn't exist, not this close to us, not with the universe's speed limit in the way. So what fired the oh my god particle at Earth, and how do you trace a charged bullet back to its trigger when space itself bends its path? By the time one of oh my god particles reaches Earth, its path has been revised by the Milky Way, the intergalactic web, and perhaps fields we have not even mapped. And still, the energy remains, stubbornly intact, demanding an explanation that fits both the source and the journey. These particles are the only samples of extreme physics we can hold, arriving free of charge, yet never free of consequence. At the highest energies, space is not empty. It is crowded with ancient light, and that light is a gauntlet. Relativity turns a gentle background into a head-on collision field, and the journey becomes as important as the launch. This is the GZK suppression, the cosmic speed limit written not on a sign, but into interactions that should shave the extraordinary down to the ordinary. If we cannot watch the particle itself, we can watch what it does to our sky. When an ultra-high-energy cosmic ray meets the upper atmosphere, the first impact erases the original. What remains is a cascade, multiplying and spreading, a brief storm of secondaries. From those patterns we infer the energy, the direction, and the mass, and each inference carries uncertainty that can masquerade as discovery. And once the measurements harden, the central question sharpens with them. What kind of astrophysical machine can push a charged particle into the Zepter, electron-volt regime without losing it to radiation, escape, or self-destruction? The candidates are dramatic. Jets from active galaxies, starburst environments, newborn magnetars, and each must pass a ruthless test of size, field strength, and time. The Hillis criterion is not a theory of how acceleration happens, but it is a gatekeeper, and most objects in the universe do not fit through it. Even those that do must still aim through magnetic fog, and leave enough survivors within a limited horizon to match what we observe. Some models do not accelerate at all. They begin with energy already stored, waiting to be released by rare decays or exotic relics. These possibilities carry a different kind of implication, because they would mean the particle is not just telling us where it came from, but what the universe is made of. Because whatever launched that particle did not send it for our convenience. It arrived as a fragment of a larger story, one we can read only by expanding our instruments and tightening our reasoning. If we succeed, we will identify nature's true cosmic accelerators and learn how the universe spends energy at its most extravagant scales. If we fail, we may learn something even more unsettling, that at the highest energies, the rules themselves can bend. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We will follow cosmic rays from their first discovery to the modern hunt for zevatrons, and to the edge where exotic physics becomes plausible. A single particle can carry the punch of a thrown baseball, yet be smaller than an atom. On one quiet night in Utah, Earth took that hit, and physics blinked. Just long enough for a mystery to slip through. For centuries the sky looked calm because our eyes missed its invisible rain. The blue dome seemed empty, yet it was threaded with charged visitors that passed through skin and stone without asking permission. Early observers noticed odd behavior in electroscopes, those delicate leaves of metal that slowly collapsed. Even when sealed and shielded, they discharged as if the air itself carried a persistent, unseen electricity. Then instruments began to count what flesh could not feel, and the atmosphere became a detector. Each ion pair, each tiny spark of broken neutrality, became a clue that the world was being quietly bombarded. In 1912, Victor Hess climbed into a balloon with electroscopes and doubt. He rose above the shielding air, watched ionization increase with altitude, and proved the radiation came from space. The logic was simple, but the risk was not. If radiation came from Earth's crust, the signal should fade as he climbed, because rock would fall away beneath him. Instead, the discharge rate climbed, especially at several kilometers up, where the air thins and the horizon widens. Hess was measuring an invisible storm at the edge of breath, an extraterrestrial influence that grew stronger with height. His flights landed in a Europe poised on the edge of war, yet the result outlived the era. In time, the discovery earned Hess a Nobel Prize, and it gave physicists a new way to interrogate the universe. That result created a new kind of astronomy, built from impacts instead of light. Cosmic rays became messengers that arrived uninvited, and they carried clues about violent engines beyond Earth. Unlike photons, these messengers were charged, and that detail changed everything. Charge means deflection, and deflection means that the sky can hide a source even while it delivers its products. Over the decades, researchers catalogued energies, directions, and rates, and patterns emerged. Most cosmic rays were modest, and their sources could be explained with familiar astrophysics. At lower energies, the flux is generous, almost comforting, and detectors click steadily. The spectrum falls like a steep hillside, meaning that each jump in energy cost an enormous drop in event rate. As detectors improved, the spectrum stretched upward into the ultra-high energy range. Each step higher forced new theories about acceleration, confinement, and the limits of magnetic fields. The basic question hardened into a challenge that sounded simple. What can accelerate a charged particle to energies no human machine can reach? In laboratories, particle accelerators use electric fields, radio frequency cavities, and carefully shaped magnets. In space, nature must do the same job without wires, using shock fronts, rotating fields, and turbulent plasma as its circuitry. By mid-century, particle physics supplied a language for the problem, and astrophysics supplied the arenas. Supernova shocks, pulsars, and active galaxies became candidate accelerators, each with constraints. A shock wave, for instance, can bounce particles back and forth across a moving boundary, gaining energy in repeated crossings. The idea is elegant, but it depends on magnetic turbulence that can trap a particle long enough to matter. The constraints were brutal, because nature must pay every energy bill. A particle must be trapped long enough to gain energy, yet not lose it to radiation or collisions. If the magnetic field is too weak, the particle's gyroradius grows, and it simply leaks out. If the field is too strong or too curved, the particle radiates away energy, bleeding momentum into photons. At the highest energies, another limit loomed, written into the universe itself. Interactions with background light should drain cosmic rays over long distances, creating a cutoff in what reaches Earth. That expectation became a kind of cosmic speed limit, not for velocity but for survivable energy. If the universe is filled with microwave photons, then ultra-energetic protons should not travel far. Those microwave photons are the cosmic microwave background, the cooled afterglow of the early universe. They are everywhere, and to an ultra-fast proton they appear blue-shifted, energetic enough to trigger reactions that steal the proton's energy. Over long voyages, a proton can collide with that photon bath and produce pions, a process that acts like friction without contact. The result is the GZK suppression, named for Greisen, Zatsepin, and Kuzmin, and it should thin the highest end of the spectrum. Still, the sky kept sending rare outliers, and the only way to learn was to build bigger eyes. The hunt moved from small counters to vast arrays that used the atmosphere as a calorimeter. Instead of catching the primary particle directly, researchers learned to read its consequences. The air itself becomes the target, and a shower becomes a luminous signature that can be measured from kilometers away. In the Utah desert, far from city lights, one such instrument waited in silence. It was called the Fly's Eye, and it was built to watch darkness for brief flashes. The name was not poetic decoration, because the design truly resembled an insect's compound vision. Many small viewing elements, each with its own patch of sky, combined into a wide-angle stare. The Fly's Eye was not a single telescope but a compound creature. It used clusters of rotating mirror cans that scanned the sky, each feeding light into photomultiplier tubes. Each mirror can was a careful compromise between field of view and sensitivity. As the mirrors swept and held their aim, they collected faint ultraviolet light that would otherwise vanish into the desert night. Those tubes could register a few photons and turn them into electrical pulses. Inside, a photon strikes a photocathode, liberating an electron, and a cascade of dynodes multiplies that electron into a measurable signal. The technique relied on faint ultraviolet fluorescence from nitrogen, excited when an air shower tears through the atmosphere. It is not a spotlight, but a thin, ghostly glow. Air molecules briefly energized, then relaxing and releasing light. A cosmic ray never arrives as a tidy bullet that hits a sensor directly. It strikes high above, triggers a cascade of secondary particles, and the shower paints a moving track of light. The first collision is a microscopic catastrophe, typically with a nitrogen or oxygen nucleus. That impact creates new particles, pions, kaons, muons, electrons, and photons, that multiply as the cascade deepens. As the shower grows, it reaches a maximum where creation and loss balance. Then it thins as particles range out. The longitudinal profile, the rise and fall of light, becomes a fingerprint of the primary's energy and type. From that track, geometry and timing can reconstruct where the primary came from and how energetic it was. The method was elegant, but it demanded careful calibration and stable skies. Timing matters because the shower is a moving line, not a static flash. Each tube sees a different segment, and the sequence of triggered pixels encodes the angle, distance, and speed of the luminous path. Dugway Proving Ground offered isolation, darkness, and wide horizons, plus the harshness that tests every cable and seal. The equipment was improvised in places, maintained by people who learned to distrust everything. In daylight, the site looks like a stripped landscape of pale soil and distant mountains, with heat shimmering above the flats. At night, it becomes a black bowl, and the stars feel close enough to touch. On clear nights, operators listened to wind and electronics, and they waited for a pattern that would not repeat. Most triggers were ordinary showers, and most nights ended without a story. Yet even the ordinary carries structure, because cosmic rays arrive in a steady statistical rain. The detector's job is to sift that rain for the one drop that falls with impossible weight. October 15th, 1991 was moonless, and the desert air was cold and dry. The fly's eye watched its sector of sky, and then the darkness lit up with an impossible signature. In the control room, the event did not announce itself with drama, only with data. A sequence of tubes fired in a coherent arc, and the pattern refused to look like noise. The event began as a streak of fluorescence that grew, peaked, and faded, consistent with a massive air shower. Its profile suggested a primary particle that had arrived with absurd energy. The light curve rose as the cascade multiplied, then rolled over as the shower exhausted itself deeper in the atmosphere. That shape, when fitted to shower models, pointed to an energy scale beyond anything previously secure. The reconstruction produced a number that made experienced researchers pause. The estimated energy was about 320 exa, electron volts, with an uncertainty near plus or minus 90. An exa, electron volt, is a billion electron volts, and the prefix is not decorative. It marks a domain where the usual intuition breaks, because the particle's energy dwarfs its rest mass by orders of magnitude. That scale is hard to hold in the mind, so translate it into human terms. It was roughly 50 joules of kinetic energy, packed into a single subatomic particle. 50 joules is not cosmic by everyday standards, but it is outrageous at microscopic scale. It is the energy of a fastball, delivered by something that should be nearly massless. If you could imagine that energy concentrated into a point smaller than a nucleus, the comparison becomes unsettling. A child can throw 50 joules, but no child can place it into a single proton and let it fly across the galaxy. Speed was not the surprise, because at these energies the particle is already near light speed. The surprise was how close it was to a photon in a race across space. Relativity makes the difference between almost and exactly meaningful. When kinetic energy grows, gamma grows, and the particle's clock and length scales distort until classical language becomes unreliable. Over a light year, the particle would lag behind light by only nanometers. That is the kind of difference that makes relativity feel less like theory and more like a trap. To picture it, imagine two runners crossing a continent, one made of light and one made of matter. After a year of travel, the matter runner arrives behind by less than the width of a virus, yet it carries a baseball's worth of punch. The data implied a visitor from far away, yet the universe should have taxed such a traveller. If it were a proton, background radiation should have bled its energy long before arrival. At energies above the expected cutoff, the mean free path shrinks, and the universe becomes effectively smaller. The question becomes geographic as well as physical. How close must the source be for the particle to survive the trip? The event also arrived alone, a single strike in a sea of lesser ones. That rarity made it precious, and it also made it suspect. Statistics can be cruel at the top of the spectrum, because the flux is so low that years can pass between candidates. When one event dominates a dataset, it can look like discovery or like a mistake, depending on your mood. The fly's eye saw it with one sight, not with a stereo baseline. Monocular detection can reconstruct a shower, but it leaves more room for geometry errors and atmospheric ambiguity. With two separated eyes, the shower track can be triangulated directly, tightening distance and angle. With one eye, the fit must infer geometry from timing and profile, and small assumptions can echo into large energies. So the first reaction was not celebration but suspicion. Was the signal real, or was it a glitch dressed up as a miracle? Every part of the chain became a suspect, starting with the photomultiplier tubes. A noisy channel, a mistimed pulse, or a saturated response could fake a bright track. Photomultipliers are exquisitely sensitive, and that sensitivity comes with quirks. Afterpulsing, gain drift, and occasional electrical discharges can mimic light, so each tube's behavior had to be audited against logs and calibration runs. Then came the mirrors and their pointing, the rotation, and the alignment. A small error in angle can inflate energy, because distance and brightness are tied together. If the shower is reconstructed as farther away than it truly was, the inferred light yield must be larger to match the observed signal. That larger light yield translates directly into a larger shower, and a larger shower means a larger primary energy. Atmosphere became the next suspect, because fluorescence depends on air density and clarity. Aerosols, thin clouds, or unmodelled scattering can distort the light profile and the inferred shower size. Fluorescence yield changes with pressure and temperature, and the transmission of light depends on Rayleigh scattering and aerosol content. In the desert, conditions can be stable, yet even subtle haze can tilt the energy estimate. Even the calibration lamps and the gain settings were revisited because desert hardware drifts. The team treated the event like a crime scene, and they assumed nothing was innocent. They checked whether the absolute light scale was correct, whether the timing electronics were synchronized, and whether any channels behaved oddly that night. They also compared the event's pattern to known shower morphologies, looking for telltale inconsistencies. They reanalyzed the geometry, the timing fit, and the longitudinal development of the shower. They tested alternative reconstructions, checked stability across tubes, and searched for inconsistencies. Different atmospheric models were tried, and different assumptions about the shower axis were explored. If the energy could be pushed down into the ordinary by reasonable choices, the miracle would evaporate, and everyone would sleep better. The process took months, then longer, because extraordinary claims demand slow arithmetic. A year of scrutiny followed, not to prove wonder, but to eliminate mundane failure. This was not only caution but culture, because cosmic ray physics has learned humility. The sky can deceive, electronics can lie, and the human mind is eager to see patterns where none exist. In the end, the track held together across independent checks. The shower profile matched expectations for a real cascade, and the systematics could not erase the energy scale. The uncertainties remained because they always do, yet the event refused to collapse into a trivial explanation. What remained was a stubborn conclusion. Something had struck the atmosphere with an energy that strained the accepted map. The community still argued, because one event cannot build a theory. Yet the data survived enough skepticism to earn a name that captured its shock. It became the "Oh my God" particle, a nickname that admitted disbelief without surrendering to it. The name spread because it summarized the feeling of encountering a number that should not exist. Nicknames are not equations, but they mark moments when scientists briefly speak like everyone else. For a second, the formal language drops away, and the human response, astonishment, takes its place. Now the story turned from detection to implication, and the implications were unsettling. If such particles reach Earth, then either their sources are nearby, or our assumptions are incomplete. Nearby sources would need to be extreme, and they would need to point back through magnetic deflection. Charged particles bend in cosmic magnetic fields, so their arrival direction is not a clean arrow. Even weak intergalactic fields can accumulate deflection over millions of years of travel. By the time a particle arrives, its path may be a scribble, and the sky position becomes a blurred hint rather than a signature. If sources are not nearby, then the GZK expectation is challenged, and the universe looks more transparent than predicted. That would force new physics, or new particle identities, or both. Perhaps the primary was not a proton, or perhaps the interactions behave differently at extreme energies. The uncomfortable possibility is that the event is a message about the limits of our models, not merely about the power of distant engines. The Oh My God event did not just extend a graph by one dot, it threatened the boundary between what astrophysics can accelerate and what particle physics can allow. That boundary is where two disciplines meet, and where each hopes the other will provide the missing piece. If acceleration seems impossible, we question the source, and if propagation seems impossible, we question the particle or the rules. It also raised a practical problem that defines the hunt to this day. How do you trace a charged messenger back to its engine when space itself scrambles its path? The atmosphere gives us a luminous record, but it is a record written in fleeting ultraviolet and reconstructed through models. Each event is a single sentence torn from a book we cannot yet read in full. In the Utah desert, the fly's eye had done its job, but it left a riddle in its wake. One particle had arrived with impossible wealth and no clear return address. The desert returned to silence, yet the data remained and the number kept its sharp edge. Somewhere, something had performed an acceleration trick that outclassed our machines, then sent the result across a universe that should have stopped it. From here, the pursuit widens, because one detector cannot settle a cosmic argument. We will follow the next generation of observatories and the theories they forced into the open. The central question remains, sharpened by that moonless night. What is shooting at Earth, and what kind of universe allows the shot to land? The Oh My God particle did not only challenge acceleration, it challenged travel because the intervening universe is not passive, and it does not merely watch a particle pass. If it was a proton, the universe itself should have stopped it, or at least shaved its energy down to something ordinary. This chapter is about a limit that is often misunderstood, even by people who know the headline. The GZK limit is not a cap on what engines can build in principle. It is a barrier to what can survive the journey to Earth, intact and still extreme. In other words, it is less about invention and more about endurance, what the cosmos allows to remain undiminished. Visually, imagine a single charged particle leaving a distant galaxy like a spark from a grinding wheel. It is not flying through emptiness, but through a sea of ancient light that fills every cubic centimetre. The question is not only how the spark was made, the question is whether the spark can cross the sea without being quenched, scattered, or forced to pay energy as a toll. In 1966, three groups reached the same grim conclusion, working from the same new cosmological picture: Kenneth Griesen in the West, Georgy Zatsepin and Vadim Kuzmin in the Soviet Union. Their names became shorthand for a cosmic veto, written into the background of space itself. It is a striking moment in science. Separate minds, separated by politics, converging on the same constraint. It is worth remembering what had just happened to cosmology. The cosmic microwave background had been detected only a year earlier, in 1965, by Penzias and Wilson, and interpreted as a relic of the hot early universe. Suddenly, the universe was not just expanding on paper, it was filled with a measurable relic field, a real bath of photons that every traveller must cross. Once that bath was real, the question became unavoidable. What does it do to the fastest particles? The logic begins with a quiet fact about space, the kind that sounds poetic until you do the arithmetic. Intergalactic space is not empty. It is filled with the cosmic microwave background, the cooled afterglow of the early universe. Those photons are ancient, older than any star, and they have been stretched by expansion into microwaves. On screen, the CMB is often drawn as a soft grain, a uniform haze behind everything. That is accurate in spirit because it is almost perfectly isotropic, with only tiny temperature anisotropies. It is also deceptive because almost uniform can still be overwhelmingly dense in photon number. Uniform does not mean sparse, and the universe is patient enough to make density matter. The CMB is cold in our frame, about 2.7 Kelvin. Its photons are low energy in the microwave band, with typical energies around a fraction of a milli-electron volt. To us they look harmless, like a thin fog of ancient light drifting between galaxies. They do not ionize atoms, and they do not burn skin, so intuition files them as irrelevant. Yet the fog has a staggering population. There are hundreds of CMB photons in every cubic centimetre of space, roughly 400 per cubic centimetre on average. That means a particle crossing intergalactic distances does not face one encounter. It faces an astronomical number of chances to collide, and probability becomes destiny when the path is long enough. But a proton at extreme energy does not share our frame. At 100 eV and beyond, its Lorentz factor is enormous. Relativity turns the same background into something else. The Lorentz factor is not an abstract symbol here, because it sets the scale of the transformation. At these energies, the proton's internal clock is slowed by orders of magnitude, and lengths along its direction of travel are contracted. In the proton's perspective, the universe is compressed, brightened, and aimed. The calm, isotropic fog becomes an oncoming wind of radiation. In the proton's rest frame, the CMB is Doppler shifted. Photons arriving head-on are blue shifted the most, while photons from behind are red shifted into near nothing. The fog becomes a beam of energetic radiation, concentrated into a forward cone. Relativistic aberration narrows the sky, forcing most of the photon flux into the direction the proton is moving toward. A useful visual is a star field that suddenly collapses toward one point ahead of the proton. The microwaves, once gentle and long wavelength, tighten into shorter waves. The color temperature climbs, not because the CMB changed, but because the proton changed frames. In that frame, the background can look less like microwaves and more like a harsh ultraviolet, or even higher energy field. This is accessible relativity in its sharpest form, and it is also deeply counterintuitive. Nothing needs to outrun light, and the proton never does. The proton only needs to see the universe rushing toward it, with the CMB photons arriving like oncoming hail. The violence is not in speed, but in the transformed energy of each encounter. The key is the center of momentum energy, which decides what reactions are possible. A low-energy photon in our frame can become a high-energy photon in the proton frame, simply because of the boost. At some proton energy, the photon can trigger hadronic reactions that simply cannot occur below threshold. The universe does not need new particles in the background, only a new perspective. Below that threshold, the proton mostly coasts. It loses energy slowly through the expansion of the universe and minor processes, and over modest distances it can remain extraordinary. Above the threshold, it starts paying a steep toll, and the toll is not negotiable. Once the reaction channels open, they open everywhere, because the background is everywhere. The toll is photopion production, a specific and well-tested channel in particle physics. A CMB photon strikes an ultra-relativistic proton. The collision has enough energy to create new particles, and new particles must be paid for with the proton's kinetic energy. The process is familiar in accelerators, but here the accelerator is the cosmos, and the target is the sky itself. You can picture the proton as a fast-moving bank account. Each time it is forced to mint a peon, it must spend a chunk of its balance. The universe does not take interest. It takes principle, and it takes it in discrete withdrawals that accumulate quickly. After enough withdrawals, the account is no longer extreme. The simplest channel is P plus gamma making a delta resonance. The intermediate state is the delta 1232. It is a short-lived excited baryon that decays almost immediately, long before the proton travels any macroscopic distance. In practice, the resonance is a spike in probability, a narrow doorway that opens wide at the right energy. In a diagram, this looks clean and almost elegant. A proton and a photon meet. A resonance briefly exists as a spike in probability. Then the resonance breaks apart into a nucleon and a pion, with energy and momentum redistributed. That redistribution is the heart of the loss, because the outgoing nucleon carries less of the original forward energy. The delta can decay back into a nucleon and a pion. One common outcome is a proton plus a neutral pion. Another is a neutron plus a positive pion, which subtly changes the story because neutrons are neutral but unstable. The branching ratios are not just bookkeeping. They determine what secondaries appear and how the energy is partitioned. That neutron channel is a reminder that proton propagation is not always purely protonic. A neutron can travel some distance without magnetic deflection, then decay back into a proton, an electron, and a neutrino. At these energies, time dilation stretches the neutron's effective range to astrophysical scales, but not enough to erase the energy loss problem. It can blur directions slightly, yet it cannot preserve the original energy indefinitely. The details matter because they drain energy fast. Each interaction typically costs the proton a large fraction of its energy because creating a pion demands a significant share of the center of momentum budget. A rough rule is about 20% lost per collision, although the exact inelasticity depends on the channel and kinematics. Even if the fraction varies, the trend is brutal. Repeated hits push the proton downward. This is not a gentle drag like air resistance. It is a stepwise degradation, a staircase rather than a slope. After a few interactions, an ultra-high energy proton is pushed below the trans-GZK regime, even if it began far above it. The universe does not need to stop the particle, it only needs to make it ordinary. The threshold sits near the scale that makes the story famous. Around 50 to 60 eV, photopion production turns on strongly. The exact value depends on angles in the photon spectrum, because not every collision is head-on. A glancing collision shifts less energy into the proton frame, and it may fail to cross the doorway. The CMB is not a single photon energy, and the proton does not meet every photon at the same geometry. There is a distribution, and so the threshold is a band, not a razor line. Still, once the proton energy is high enough, the band becomes unavoidable. The tail of the photon spectrum and the statistics of head-on encounters conspire against long survival. Above that, the cross-section rises around the delta resonance. Higher resonances and multipion channels follow at greater energies, widening the set of ways energy can be lost. The proton is now moving through a minefield of background photons, where minefield is a statistical statement, not a metaphor. The danger is not a single catastrophic event, but the inevitability of repeated interactions. A visual cue helps here. Imagine the proton's path as a glowing line through a dark volume. Along that line, flashes occur at random intervals. Each flash is a collision, each collision a sudden shedding of energy into new particles. Some flashes are brighter, some dimmer, but the overall trend is downward, like a signal fading with distance. The CMB is everywhere, so the minefield is everywhere. There is no route around it, no empty corridor between galaxies that lacks the background. The only escape is distance, because distance determines how many chances the universe has to collect its toll. In this sense, space itself behaves like a filter that depends on energy. If the source is close enough, the proton can arrive before it is degraded. If the source is far enough, the proton's original energy becomes a rumour. By the time it reaches us, it will have been edited by physics. The universe, in effect, rewrites the message while the messenger is still in flight. This is where the GZK horizon enters, and the word horizon must be handled carefully. It is a propagation horizon, not a geometric boundary. It is the effective maximum distance from which a trans-GZK proton can reach us with most of its energy still intact. Beyond it, the probability of arriving still extreme collapses. The horizon is set by the mean free path and the energy loss length. Those lengths shrink as energy rises, because the proton sees a more intense and more energetic photon field. At a few times 1020 eV, the universe becomes small in a very literal sense. The cosmos may be vast, yet the usable distance for extreme protons becomes a local bubble. For protons above the GZK threshold, the horizon is on the order of 100 megaparsecs. That is roughly 360 million light-years. In cosmology, that is local neighbourhood distance, a small bubble carved out of an immense observable volume. It is the difference between anywhere in the universe and nearby enough to matter. Local does not mean easy, and it does not mean empty. 100 megaparsecs contains many galaxies and clusters, filaments of the cosmic web, and large-scale structure that astronomers map in redshift surveys. It contains the familiar scaffolding of matter, the places where gravity has gathered galaxies into knots. Yet it is still a tiny fraction of the observable universe, and it sharply limits plausible sources. This is the emotional pivot of the GZK argument. It takes a particle that seems to come from out there and forces it into near here. It turns the sky into a constrained map, where only certain neighbourhoods are allowed to speak at the highest energies. The sky is no longer a blank canvas, it becomes a shortlist. The dread comes from what the horizon implies for the most extreme events. If the oh my god particle was a 320 eV proton, it should not have crossed the cosmos. It should have been bled down long before reaching the Milky Way, losing energy in repeated photopion steps. The higher the energy, the more quickly the universe insists on lowering it. At 320 eV, the energy loss length is especially short. The proton would interact repeatedly with the CMB, and the probability of avoiding interactions over hundreds of megaparsecs becomes vanishingly small. Its energy would cascade downward toward the cutoff, like a ball bouncing down a staircase. Each bounce is a paean, and each paean is a measurable subtraction. So the event forces a geographic demand that feels almost like an accusation. The source must be within the GZK horizon. It must also be capable of accelerating to ZeV energies, a Zevitron-class engine, because you do not arrive at 320 EeV by accident. Even if the observed energy is uncertain by tens of percent, the conclusion remains uncomfortable. That combination is brutal. Nearby sources are limited in number, and ZeV-capable accelerators are not common even in theory. The universe is full of galaxies, but not every galaxy contains a machine that can fling a proton to a few hundred EV. The Hillis-style requirement, size and magnetic field strong enough to confine the particle, narrows the field dramatically. This is where the sky becomes uncomfortable. The arrival direction of the Oh My God event does not point to an obvious nearby powerhouse. There is no clear active galaxy or cluster candidate sitting in that patch, no bright beacon that makes the mystery feel resolved. The direction looks at first glance like an absence rather than a clue. In visual terms, we can place a translucent sphere around the Milky Way, marking the 100 megaparsec neighbourhood. Then we can drop pins for known active galactic nuclei, radio galaxies, and rich clusters, letting the viewer feel the density of candidates. The uncomfortable part is the empty feeling in the direction that matters, an island of quiet where we expected noise. Even if there were a candidate, charged particles do not point cleanly. Magnetic fields in the galaxy and between galaxies bend trajectories, and the bending accumulates over distance. Deflection can smear a source over many degrees, turning a precise direction into a region of suspicion. The sky becomes a distorted map, where the straight line is rarely the true path. The bending depends on rigidity, which is momentum per unit charge. At a fixed energy, a proton is more rigid than a heavy nucleus with higher charge, and it resists bending more strongly. That is why composition matters, and why the same sky can look sharp or blurred depending on what the primary is. Rigidity is the difference between a thrown spear and a drifting leaf, but deflection is not a free pass. At 320 EeV, a proton is so rigid that it should not be bent too much by typical fields, especially if those fields are weak and turbulent. A large deflection would require stronger fields, more coherent fields, or longer path lengths that accumulate small bends into a large one. Each of those requirements has consequences elsewhere in the story. Longer path lengths worsen the GZK problem. A tangled route increases time and distance in the photon fog. The proton would lose even more energy before arrival, and the very mechanism that hides the source would also erase the particle's extremeness. The cosmos cannot both scramble the direction strongly and preserve the energy easily. So the story tightens into a paradox. The particle seems too energetic to have travelled far, yet its direction does not advertise a nearby accelerator of the required class. This paradox is not just a narrative hook, it is a collision between two kinds of knowledge: particle physics measured in laboratories and astrophysics inferred from distant light. The GZK argument uses both, and it fails only if one of them breaks. That is why the tension feels sharp. The ingredients are conservative, and the conclusion is still unsettling. There are ways to soften the contradiction, and each one carries its own cost. One possibility is that the source exists but is hidden or misidentified, perhaps because our catalogues are incomplete. It could be a faint active nucleus, a dormant black hole with occasional outbursts, or an unusual transient that was bright only briefly. In that case, the sky looks empty only because we looked at the wrong time. That idea has a visual logic. A galaxy can look ordinary in visible light, yet hide a compact engine behind dust, or radiate mostly in bands we did not monitor at the right time. Jets can be misaligned, and beaming can make a powerful object look quiet from our angle. In a universe of incomplete surveys, no obvious source is not the same as no source. But the energy requirement is unforgiving. Whatever the engine is, it must confine charged particles long enough to accelerate them, and it must do so without bleeding energy away through synchrotron radiation or collisions. The magnetic and size scales implied by such acceleration are extreme, and not many objects qualify. The engine must be both powerful and efficient, not merely dramatic. Another possibility is that our magnetic maps are wrong. Intergalactic fields are poorly measured, and even galactic fields have structure that is difficult to model, especially in the halo. A structured field could bend paths more than expected, hiding the true source direction behind a magnetic mirage. In that case, the particle's apparent direction is a lensing artifact made of magnetism. One can imagine the cosmic web threaded with weak magnetism, stretched along filaments and compressed in clusters. A particle could drift along those structures, guided like a bead on a wire, arriving from a direction that is not the direction of origin. The path could be curved, segmented, and shaped by regions we barely observe. Yet the same guidance that bends also delays, and delay carries a cost. Yet stronger or more extended fields can also trap particles. Trapping increases travel time and exposure to the CMB. That makes the survival problem worse, not better, because the proton spends longer inside the very bath that drains it. The universe does not care whether the path is straight. It only counts how many interactions can occur. Another escape is composition, and here the story becomes more nuanced rather than simpler. If the primary was not a proton, the interaction picture changes, and the relevant thresholds shift. Heavy nuclei face photodisintegration on background light, which can be even more severe than photopin production. Instead of making pions, the nucleus can be broken apart. A nucleus can absorb a photon and eject nucleons, often through a giant dipole resonance. It can fragment into lighter elements step by step, shedding protons and neutrons like sparks. That process can also impose a horizon, sometimes shorter than the proton horizon at similar total energy. The nucleus may arrive not as itself but as a family of fragments with lower energy per nucleon. So composition is not an automatic rescue, it shifts the problem into a different channel, and it changes deflection too because higher charge means stronger bending. A heavy nucleus could be more easily scrambled by magnetic fields, and the lack of a clear directional source might feel less troubling. But its survival against background light could be worse, because the nucleus has internal structure that can be broken apart. If the particle was a heavier nucleus, its path could be more scrambled, and the lack of a clear directional source might feel less troubling. But its survival against background light could be worse, because the nucleus has internal structure that can be broken apart. The paradox changes shape but does not vanish, and the sky remains constrained by propagation physics. There is also the possibility of a neutral primary, which sounds like a clean solution until you look closely. Neutrinos travel through the CMB without photopion losses because they barely interact at all, even at extreme energies. Photons at these energies pair produce and cascade, and they also face horizons set by other background fields. Neutral messengers evade magnetic bending, but they face their own detection and propagation signatures. Neutral candidates raise other problems. Neutrinos interact too weakly to make ordinary air showers easily, so producing a fly's eye, like shower, would be unlikely without special circumstances. Ultra-high energy photons would produce different shower signatures, and they would be degraded by interactions that feed electromagnetic cascades. The atmosphere itself becomes part of the diagnostic, because different primaries develop differently. The fly's eye profile favoured a hadronic primary, based on how the shower developed through the atmosphere. That points back toward protons or nuclei, because hadrons generate a characteristic mix of secondary particles and muons. The GZK logic then returns with full force. If the messenger is hadronic, the CMB is waiting. So the GZK limit becomes a filter on the sky, and it also becomes a prediction about the energy spectrum. It says the highest energy events must come from nearby, because distant sources cannot contribute at the top end. It also says their spectrum should show a suppression above the threshold, because the universe edits the highest energy tail first. The prediction is statistical, not absolute, which makes it both powerful and subtle. Later observatories would indeed see a suppression consistent with GZK expectations, which is a quiet triumph for the 1966 reasoning. But a suppression is not a total cutoff, and the universe is large enough to produce rare outliers. Rare events can still appear, and each one demands an explanation that respects the same physics. Every extreme event becomes a test of whether the filter is working as expected. The oh my god particle sits at the extreme edge. Its energy is well above the threshold. It is not just trans-GZK, it is deep into the regime where the universe should be opaque, in the same way a thick atmosphere is opaque to certain wavelengths of light. The comparison is apt because opacity is about interaction probability, not about intention. The word opaque is not metaphor here. The CMB becomes a target field, and the proton's rest frame turns microwaves into pion-making photons. Space becomes a calorimeter that strips energy away, converting a single particle's motion into a spray of secondaries. Energy does not disappear. It is redistributed into pions, gamma rays, electrons and neutrinos. Visually, we can slow time and watch the chain. A proton hits a photon, a delta resonance flares, and a pion peels away. The pion decays into gamma rays or muons and neutrinos, and the energy spreads into channels that do not keep the original direction. The original particle's clean identity dissolves into a small cascade, repeated again and again. This is the cosmic speed limit in its real meaning. The proton's speed is still below light, and it is always below light, even when the energy is mind-bending. The limit is on how much energy it can carry across long distances, because energy is what gets spent in making new particles. The universe is not stopping the motion, it is taxing the extremeness. That distinction is the heart of the misunderstanding. People hear limit and imagine a barrier to motion, like friction or a maximum velocity. The GZK limit is a barrier to endurance, how long an ultra-energetic state can persist while crossing a photon-filled universe. It is a limit written into the medium of space, not into the imagination of engineers. The paradox forces a choice that defines the documentary's central question. Either we are missing nearby astrophysics, or we are missing something in the physics of propagation. The discomfort comes from how conservative the underlying ingredients seem, because both relativity and particle interactions are well tested. When conservative ingredients produce an impossible-seeming outcome, the tension becomes unavoidable. If it is missing astrophysics, then there must be local zevatrons. They might be rare, transient, or electromagnetically quiet, and their signatures might be subtle in traditional surveys. They might hide in catalogues as ordinary galaxies, or appear only in radio or high-energy bands that were not surveyed deeply enough. The local universe could be more active in particles than it looks in light. That possibility invites a practical question. If a local engine can accelerate to ZeV energies, why does it not announce itself more loudly? Is it possible for an accelerator to be powerful in charged particles, yet subtle in photons, like a machine that leaks messengers we do not easily see? Or are we simply not looking with the right instruments, at the right cadence, in the right bands? If it is missing physics, then the interaction picture could change at extreme energies. The cross-sections could differ, or the effective thresholds could shift, altering the energy loss length in a way that matters. The background fields could be altered in ways we have not accounted for, and even relativity could be tested in a regime we cannot reproduce on Earth. The appeal here is not drama, but the possibility of a controlled inconsistency. Broken relativity is the most dramatic option, and it is not invoked lightly. The GZK argument relies on Lorentz transformations and well-tested particle physics, including the kinematics that set reaction thresholds. If the transformation rules shift, the threshold could shift too, and the cosmic veto could weaken. The universe would then be offering a rare laboratory for fundamental principles. Even then, the burden is high, because the same transformations explain countless observations, from accelerator experiments to astrophysical spectra. Any modification would need to be subtle at low energies, and only emerge at the top end. The universe would be telling us that the rules are not wrong, but incomplete. That is a narrow path, and it demands careful evidence. There are also intermediate possibilities that keep the narrative grounded while still unsettling. The primary could be an exotic particle with different interactions, or a decay product of something even more energetic produced nearby in the dark. In that case, the journey is short, but the origin is strange. The paradox would move from propagation to provenance, trading one discomfort for another. Each possibility has a signature, and signatures are what turn mystery into science. Some would predict accompanying neutrinos, arriving from similar directions because pions and muons naturally make them. Some would predict anisotropy toward local structure, such as nearby clusters or filaments, because the horizon forces locality. Some would predict a different mix of shower depths and muon content, which modern detectors can test with far greater statistics. For now, Chapter 2 leaves the problem sharpened, not solved. The universe should be opaque to the highest energy protons, given the omnipresent CMB and known hadronic physics. Yet at least once, something arrived as if it were not. That as if is where the mystery lives, between what should happen and what apparently did. The next step is to treat the sky like a crime scene with constraints. The GZK horizon shrinks the suspect list to the local universe. Magnetic deflection blurs the fingerprints, and composition muddies the footprints. Even the absence of obvious sources becomes a clue, because it tells us where our expectations fail. We are left with a tension that is almost philosophical, but it is anchored in measurable quantities. How can one particle carry so much energy across so much space, when space itself is filled with a field that should take that energy away? What does it mean for the universe to be transparent at one energy and opaque at another? And if the cosmos can veto certain journeys, what other vetoes are hidden in plain sight? The central question returns with higher stakes. What engine can produce such energy, and how can a charged messenger keep it across a hostile cosmos? The oh my god particle is not only an event, it is a stress test for our picture of the nearby universe and for the propagation physics we thought we understood. By the end of this chapter, the dread has a clear shape, and it is more specific than wonder. Either the source is close and hidden in plain sight within a few 100 million light years, or the rules we trust at lower energies are bending at the top, where our laboratories cannot follow. The discomfort is that both options are plausible enough to take seriously. The oh my god particle becomes a fork in the road, and both paths are unsettling. One path leads to missing astrophysics in our cosmic neighbourhood, implying nearby engines we have not properly recognised. The other path leads to broken physics at the edge of the known spectrum, implying the universe has kept a secret until now. The oh my god particle could have been a lonely glitch, a single spike in the record that never repeated, and for a while that possibility hung over the field like a verdict. In the early 1990s, ultra, high-energy cosmic ray physics still lived with fragile statistics, because the rarest events arrive on human timescales. The next decade would decide whether the Utah shower was an error or the first specimen in a new class. After 1991, the spectrum's top end stayed thin but provocative, like a cliff edge with a few footprints beyond it, and every footprint invited a new argument. A few more candidates appeared, each one forcing the same questions about travel, energy, and return address. If the universe truly imposed a cutoff, why did the data keep whispering about exceptions, quietly, stubbornly, and just often enough to be dangerous? At these energies, the numbers themselves become part of the drama, because the units stop feeling like bookkeeping and start feeling like a physical threat. An exa, electron volt, is 10 to 18 electron volts, and a 200 eeV particle carries macroscopic punch in microscopic form. It is the kinetic energy of a thrown baseball compressed into a single atomic nucleus, and that contrast is hard to forget. Another way to say it is that nature has built a particle accelerator far beyond anything humans can engineer, then aimed it at Earth. Those comparisons are not just rhetorical, because they highlight what is strange about the messenger. A baseball's energy is distributed across trillions of atoms moving together, while an ultra, high-energy cosmic ray concentrates that energy into one charged projectile. When it strikes the upper atmosphere, it does not merely collide, it detonates a cascade, and the cascade becomes the only evidence we will ever hold. The primary is gone in a fraction of a microsecond, and the atmosphere becomes a temporary detector. The field needed a different kind of instrument to settle the argument. Fluorescence eyes were powerful, yet their duty cycle was limited by darkness and weather, which is a polite way of saying they spend most of their lives blind. They watch the sky like astronomers, but only on clear moonless nights, and cosmic rays do not schedule their arrivals. Even the best fluorescent systems live under a ceiling of practical constraints, because the sky is not a laboratory. Fluorescence detection also asks the atmosphere to cooperate, and the atmosphere is an unreliable partner. The ultraviolet glow is faint, produced when nitrogen molecules are excited by the shower's charged particles, and then relax by emitting photons. Aerosols, humidity, and thin clouds can dim that glow without warning, and the dimming can mimic a lower energy shower. Even when the shower is real, the light can lie about how much energy was actually deposited, unless the air is monitored with almost obsessive care. There is also a subtlety that matters at the highest energies, because the fluorescence method is calorimetric but not complete. The telescopes see the energy that goes into ionization and excitation, yet some energy escapes as neutrinos and high-energy muons that reach the ground. Analysts correct for that invisible energy, but the correction depends on interaction models and composition assumptions. In other words, even the most direct method still carries a model-shaped shadow. Japan's answer was blunt and statistical. Build a huge surface array that never sleeps, then wait for the rarest showers to hit. It was an engineering philosophy as much as a scientific one, and it carried a certain austere confidence. If the flux is 1 particle per square kilometre per century at the top end, then the only honest response is scale. Instead of chasing perfect individual events, The strategy was to accumulate exposure until the universe had no choice but to speak. Agartha arrived as a grid of particle detectors spread across open ground, laid out like a quiet, instrumented plane that could be mistaken for emptiness from a distance. Each station waited for the same thing: a sudden rush of secondary particles, a thin front moving at nearly light speed. When it came, the array would not see a track in the sky, but a pattern stamped onto the Earth. The shower would announce itself as synchronized clicks, separated by kilometers, but tied together by timing. Visually, a surface array is almost anticlimactic, and that understatement is part of its character. There are no domes, no mirrors, and no giant lenses, only boxes and cables under open air, enduring sun, snow, and wind. Yet the simplicity hides a powerful idea. Turn the ground into a sampling screen, and let the shower write its own signature. The Earth becomes the paper, and the cascade becomes the ink. Agartha sampled the shower front at the surface, using timing and density to infer the primary, and the logic is geometric as much as it is physical. The arrival times across the grid define a tilted plane, and that plane points back toward the incoming direction. The particle densities falling with distance from the core provide a handle on size, and size is a proxy for energy. The reconstruction is a translation from scattered local measurements into a single coherent event. That translation depends on a concept that sounds simple, but hides a lot of physics: the lateral distribution function. The shower core is dense, packed with electrons, positrons, photons, and muons, while the outskirts are a thinning spray that still carries directional information. By fitting how the signal falls with distance, the array estimates what the shower would look like at a standard radius, then converts that to energy. It is an inference built on patterns, and patterns are only as trustworthy as the models beneath them. Surface arrays trade direct calorimetry for exposure, and that trade is the entire strategy. They see day and night, they ignore moonlight, and they tolerate ordinary weather, which turns time itself into a scientific asset. They win by collecting enough area times enough years until the rare becomes inevitable. In a field where the flux collapses at the top end, inevitability is the closest thing to certainty. But the trade has consequences that matter at the top end, because the last decade of the spectrum is where assumptions become leverage. A surface array does not watch the shower grow, so it must rely on models of hadronic interactions. Those models extrapolate beyond accelerator energies, and the extrapolation is a quiet source of uncertainty. The first interaction happens at center of mass energies beyond the reach of terrestrial colliders, so nature is testing physics in a regime we cannot reproduce. By the early 1990s, that uncertainty was no longer an abstract concern, because the stakes had become existential for the anomaly. The community had one spectacular event from Utah, and it needed a second anchor point. It needed something that looked robust in a different instrument, built by a different team, under a different sky. Confirmation in science is rarely romantic, but it is often decisive. In 1993, Agartha reported a clean event near 200 exa, electron volts, and the number landed with weight that was felt far beyond Japan. It was not a marginal bump, and it was not a single phototube track, vulnerable to a calibration quirk. It was a surface pattern with multiple stations firing in a coherent sequence. The event looked like a real shower crossing real ground, leaving behind a measurable geometry. The reconstruction leaned on many stations triggering within microseconds, each one confirming the same wavefront as it swept across the array. The shower footprint was large, spreading across the grid like a fast-moving weatherfront that does not care about borders. The timing fit was stable, and the energy estimate stayed extreme even when analysts stressed the assumptions. Even when they pushed the models, the event refused to become ordinary. A surface array event also has a particular visual logic, and it translates well to the screen. You can imagine a map of the grid, dots lighting up in order, the earliest stations forming a line that hints at direction. The core is a bright center, and the density falls outward in rings that are never perfectly symmetric. The asymmetry is not noise, it is the imprint of angle, altitude, and the messy details of the first collision. That event changed the social meaning of the anomaly, which is a real force in science even when no one wants to admit it. One impossible dot can be doubted, because instruments fail and coincidences happen, and careers are built on skepticism. Two begin to look like a population, and a population demands an explanation rather than a shrug. The story shifted from "did it happen" to "what could possibly do this?" Agartha's result did not end the GZK argument, and in a way it made the argument sharper because it raised the cost of dismissal. The universe still looked hostile to protons above the cutoff because the cosmic microwave background is everywhere, filling space like a cold, ancient fog. A proton that energetic should collide with background photons often enough to bleed energy over tens of megaparsecs. The higher the energy, the more the proton sees those photons as dangerous targets. The GZK effect is simple in outline but brutal in implication, because it turns empty space into an active medium. Above roughly 50 eV, a proton can produce pions when it hits a CMB photon in its rest frame, crossing a threshold set by relativistic kinematics. That interaction steals energy efficiently, and the energy loss length collapses, turning the cosmos into a short-range medium. The universe becomes a kind of attenuating filter, allowing only nearby extremes to survive. Now the paradox had company, and company makes a paradox harder to ignore. If multiple trans-GZK events were real, then either the local universe hid accelerators, or propagation physics was incomplete. Either way, the sky was no longer a passive backdrop because it was shaping what could reach us. The question was no longer only what accelerates, but also what allows passage. The next years became a tug-of-war between datasets, and the tension was not merely academic, because it touched the credibility of entire methods. Some experiments saw a suppression consistent with GZK, while Agassi's spectrum looked flatter at the top. The difference was small in absolute counts, but enormous in interpretation. When you are arguing over a handful of events, each dot on a plot carries disproportionate power. Systematics became part of the plot, because energy is not measured directly, and the shower is a translation rather than a photograph. Energy scales differed by tens of percent, and at the steep end that difference can create or erase a handful of headline events. When the flux drops like a power law, calibration becomes destiny. A small shift in scale can move an event from forbidden to merely rare. There were also differences in methodology that mattered in subtle ways, and those subtleties became battlegrounds. Surface arrays infer energy from ground signals at a reference distance, then convert that signal using simulations that embed assumptions about composition and interactions. Fluorescence detectors infer energy from light yield, then correct for invisible energy carried by neutrinos and muons. Both approaches are principled, yet both are vulnerable to different kinds of ignorance. Yet the deeper point survived calibration debates, and it did so stubbornly, because it was anchored in repeated extremes. The sky was capable of delivering particles well above 100 eV, and it did so more than once. Even if the precise energy shifted, the existence of the extreme tail did not vanish. The menagerie was small, but it was alive. That forced a new ambition that sounded simple and proved brutal. Turn cosmic rays into astronomy, then point back to the engines. The dream was older than Agassa, because charged particles were discovered before gamma-ray astronomy matured, and the temptation to trace them home is almost irresistible. The obstacle was also older, because magnetic fields were always in the way, quietly rewriting trajectories across the cosmos. The universe offers messengers, but it rarely offers straight lines. Charged particle astronomy fails for the same reason it is tempting, because charge is both a gift and a curse. Charge means magnetic bending, and magnetic bending means the sky lies about directions. A cosmic ray does not travel like a photon, because it does not respect straight lines in a magnetized universe. Even at extreme energies, it can arrive with its history partially erased. Deflection depends on rigidity, which is momentum divided by charge, and that ratio is the key that connects particle identity to navigational honesty. At the same energy, a proton has high rigidity, while iron has 26 times less, because its charge is 26. The same total energy can therefore correspond to very different deflection angles. In practical terms, composition determines whether the sky is a map or a maze. Energy helps, but charge can erase the advantage, and this is where intuition often breaks for non-specialists. A 200 eeV proton may bend only a few degrees in plausible galactic fields, which is small enough to keep source hunting alive. A heavy nucleus can wander far, arriving from a direction that feels unrelated to its birthplace. The same shower energy can therefore hide very different paths. The Milky Way's magnetic field is structured and uncertain in the halo, which is exactly where incoming particles first encounter it, like a ship meeting coastal currents. In the disk, spiral arms and turbulence create a complicated lens that can focus or defocus trajectories. In the halo, the field may extend in large-scale patterns that are still debated, partly because we infer them indirectly from Faraday rotation and synchrotron emission. The field is real, but our map of it is incomplete. Extragalactic fields are weaker on average, yet they act over vast distances, and distance is a multiplier that never sleeps. A nanogas field sounds negligible, but over tens of megaparsecs it can accumulate influence. The universe is not empty space, but a web of filaments, sheets, and voids threaded by magnetism. Even the voids are not field-free, they are merely field-poor. Even small fields can matter when paths are long, because deflection is cumulative rather than dramatic. A particle can accumulate many tiny kicks, turning a straight line into a slow random walk, and the randomness is directional rather than energetic at first. The image is not of a sharp turn, but of a gradual wandering that only becomes obvious after millions of light years. By the time it reaches us, the original arrow may have become a smudge. The random walk is not only angular, and that detail sharpens the stakes in a way that is easy to miss. It also increases path length, and extra path length worsens energy losses against background light. A longer journey means more chances to collide with photons, and more chances to arrive diminished. The universe can blur direction and drain energy in the same breath, so direction and energy are coupled in an uncomfortable way, and this coupling haunts every backtracking attempt. The more the universe scrambles the path, the more it taxes the particle, and the more it limits how far the source can be. A particle that looks energetic at Earth may have started even higher, or it may have taken a shorter, luckier route. In either case, we're reading the end of a story, not the beginning. Cosmic ray astronomy therefore becomes an inverse problem, not a simple pointing exercise, and inverse problems are famous for humility. We observe a shower at Earth, then infer a distribution of possible histories, constrained by physics but widened by uncertainty. The data arrive as a single footprint in air and electronics, while the cause lies somewhere in a three-dimensional magnetized neighborhood. The gap between footprint and cause is where the mystery lives. The modern era built instruments designed for that inversion, combining exposure with cross-checks, because no single technique is trustworthy at the extremes. In the Utah desert, the telescope array expanded the surface grid idea and paired it with fluorescence stations. It was built to watch from above and sample from below, then reconcile the two views. The design is a deliberate response to the arguments Agasa helped ignite. Hybrid detection tightened geometry and energy, and it did so in a very practical way that shows up in the reconstructions. Surface timing anchored the shower axis with many clocks on the ground, giving a precise plane and a precise arrival direction. Fluorescence tracked development through the atmosphere, revealing where the cascade grew and where it peaked. Together, they reduced the freedom that models would otherwise exploit. When both systems see the same event, the shower becomes less ambiguous, and the improvement is more than incremental. The axis is constrained by timing and by the track of light, reducing degeneracies in distance and angle. The energy scale can be cross-calibrated, and disagreements become diagnostic rather than fatal. Hybrid events become the field's internal audits, rare but invaluable. The telescope array also inherited the emotional geography of the story, and geography matters when a narrative is built on rare lightning strikes. Utah was where the oh my god particle struck, and the desert still felt like a listening post. The landscape is wide and spare, and at night the sky looks close enough to touch. In that darkness, the instruments feel less like machines and more like sentries. In visual terms, the array reads like a quiet city of sensors, arranged with a kind of patient regularity. Small stations sit along dirt roads, each one with scintillators waiting for charged particles, their electronics humming in the heat haze. On the surrounding ridges, fluorescence telescopes stare into darkness, their cameras ready to catch a faint ultraviolet brushstroke. The scene is both mundane and cosmic, a frontier town built for invisible visitors. On May 27, 2021, the array recorded another extreme event near 240 EeV, and the number again carried a shock that was both scientific and visceral. It was quickly nicknamed the Amaterasu particle, after a Japanese sun goddess, and the name carried a deliberate echo of earlier astonishment. The name was symbolic, but the measurement was a hard statistical object. It was a shower reconstructed by modern methods, with modern cross-checks, in the same desert that started the legend. A single event at that energy is rare enough to matter, and common enough to demand context, which is a strange balance to strike. It is rare because the flux is vanishingly small, and the detector must wait years for a single candidate. It is common enough because if one appears, others may follow, and theories must survive repetition. The universe does not give us many trials, but it gives us enough to keep us honest. Amaterasu looked like a successor to the earlier shock, and that resemblance was not only in energy, but in what it threatened to imply. It revived the question of whether trans-GZK events are a tale or evidence of special sources. Are we seeing the far end of ordinary astrophysics, or the signature of something exceptional? If the answer is ordinary, then ordinary must be far more powerful than we have assumed. The first instinct was to draw a line back on the sky, because humans are built to connect dots, and astronomy is built on pointing. The reconstructed arrival direction pointed toward a region with an unsettling reputation, not because it was famous, but because it was quiet. It was not a bright cluster or a celebrated active galaxy, but a comparatively empty patch. The emptiness felt like an accusation. Backtracking through magnetic models suggested a path toward the local void, and the phrase itself carries a chill, as if space has holes. That is a nearby volume of space that is notably poor in galaxies, a depression in the local large-scale structure. In maps of the cosmic web, it appears as a pale gap amid brighter filaments. It is not a void in the absolute sense, but it is a void in the way that matters to source hunting. The void is not perfectly empty, yet it is sparse compared to filaments and clusters, and sparsity changes expectations. Dwarf galaxies and diffuse gas can inhabit it, and dark matter still shapes it, because gravity does not care about brightness. For a particle that demands a powerful engine, sparsity feels like absence, and absence feels like contradiction. If you need a furnace, why point toward a cold room? The local void puzzle is therefore psychological and physical, and both aspects matter for how the field reacts. The required power is extreme, but the apparent neighborhood looks quiet, and quietness is not what we associate with acceleration. If the source must be within a GZK limited horizon, why does the backtrack direction point toward a cosmic underdensity? Is the void hiding something, or is our line of sight being bent? To appreciate the mismatch, it helps to remember what an accelerator must do, in terms that are both technical and plain. It must confine charged particles long enough to push them to enormous energies, which requires strong magnetic fields and large size, as captured by the Hillis criterion. In plain terms, it must be a big, violent machine, not a subtle one. Confinement is the price of acceleration, and the price rises with energy. If the source is in the void, it must be unusual, or it must be hidden in an unexpected way, and those are different kinds of mystery. It could be a faint active nucleus, a hidden jet, or a transient that left a little electromagnetic trace by the time we looked. It could also be an object we do not catalogue well because it is dim, dusty, or short-lived. The particle may be announcing a phenomenon that light does not easily announce. If the source is not in the void, then the void direction is a mirage, produced by propagation rather than geography, and mirages are familiar in magnetized media. That mirage could be produced by magnetic deflection, or by misidentified composition, or by both at once. The arrival direction is an observation, but the origin direction is an inference. The inference is only as good as the assumptions that steer it. Composition becomes the plot twist because it changes two things at once, and it changes them dramatically, like swapping both the compass and the map. It changes how far the particle can point and how it survives the background light. A proton and an iron nucleus can share total energy while living very different lives in transit. The same shower can be a clean arrow or a scrambled rumour, depending on what the primary was. A proton at 240 eV is rigid and comparatively honest about direction, at least in the most optimistic field models, and that honesty is what makes source hunting tempting. A heavy nucleus at the same total energy is less rigid and more easily misdirected, because its charge is larger. The same observed shower energy can therefore correspond to very different angular uncertainties. The sky can look precise while being fundamentally ambiguous. Heavy nuclei also propagate differently, and the difference is not a minor correction that can be tucked into an error bar. Instead of losing energy mainly by photopion production, they can photodisintegrate and shed nucleons, because background photons can excite nuclear resonances. Background photons can knock the nucleus apart, reducing its mass number step by step. The particle is not just slowed, it is chemically altered. That fragmentation changes the identity of the messenger mid-flight, which is a subtle and unsettling idea when you're trying to backtrack. The particle that arrives can be a remnant, and its charge can change along the path, which changes its rigidity and therefore its deflection history. A nucleus can start as something heavy and arrive as something lighter, carrying a different rigidity than it began with. The messenger can evolve while travelling, and we only see its final form. Charge-changing propagation complicates backtracking, because the magnetic history depends on what the particle was at each stage, not only what it is at detection. It is not only what it is at detection, but what it was during each segment of travel, through each magnetic patch. In effect, the universe can rewrite the particle's steering wheel while it is already on the road. That is why a single arrival direction can never be treated as a simple arrow. Even if the primary stays intact, a heavy nucleus can fake a void origin, and that possibility keeps the story open in a disciplined way. Larger deflection can move an apparent direction away from the true source, and the displacement can be large enough to cross from filament to void. The sky location we plot may be a displaced shadow, not the lamp itself. The void may be a projection, not a birthplace. That keeps certain candidates alive, even when the naive line points elsewhere, and it keeps the narrative from collapsing into a single interpretation. Starburst galaxies like Messier 82 remain plausible because they are powerful, nearby, and rich in shocks and winds. In a starburst, supernovae overlap in time, and their collective outflows can drive large-scale turbulence. The environment is not one accelerator, but many accelerators stacked together. M82 sits in a busy local environment, not in a void, and that contrast is part of its appeal and its tension. If deflection is large enough, an event can arrive from a quiet patch while originating in a loud one, and the loudness can be hidden by magnetism. The particle would carry the energy of violence, but not the direction of violence. That is the central frustration of charged particle astronomy. But large deflection is not free, and the cost is measurable in other ways, which is why the hypothesis is testable rather than poetic. It implies stronger or more extended magnetic fields, or a heavier charge, and each option has consequences that propagate into the data. Stronger fields imply more isotropization, while heavier composition should leave signatures in shower development. The universe cannot hide its tricks without leaving fingerprints. This is where modelling becomes a character in the story, not a background tool that politely stays off camera. The data are sparse, the uncertainties are large, and the inference must be probabilistic rather than declarative. A single event cannot dominate the universe, but it can constrain the space of plausible universes. The goal is not certainty, but discipline narrowing. Researchers now use statistical and propagation frameworks that accept ambiguity, because pretending otherwise would be dishonest and ultimately unproductive. They do not claim a single line to a source, and they output a 3D constraint volume, shaped by fields, losses, and composition. The result is more like a cloud of probability than an arrow. In visual terms, the sky becomes a heat map rather than a pinpoint. One approach is approximate Bayesian computation, which is designed for problems where the likelihood is hard to write down, especially when the forward model is complex. It simulates many universes, keeps the ones that resemble the observed event, then updates beliefs about origins. In plain language, it asks what kinds of worlds would naturally produce what we saw. It is inference by controlled imagination, bounded by physics. In these simulations, extragalactic magnetic turbulence is often modelled as a Gaussian random field, which is a mathematically controlled kind of randomness that can still be summarised. That field has a coherence length and strength that can be varied, and those parameters shape the character of deflection. The coherence length sets the scale of magnetic patches, while the strength sets the size of each kick. Together, they determine whether the path is gently curved or thoroughly scrambled. The particle is then propagated through that stochastic magnetized web step by step, interaction by interaction, with energy losses and fragmentation treated as part of the same journey. Each run produces a different deflection history, even for the same nominal source direction, because turbulence makes the universe a dice throw. The same candidate source can therefore generate a family of arrival directions, not a single point. The family can be narrow for protons and broad for heavy nuclei. Energy losses are folded into the same journey, because they cannot be separated from geometry without lying to ourselves. For protons, photopion production and pair production drain energy, and the rates depend on energy and distance in a strongly nonlinear way. For nuclei, photodisintegration changes the charge and mass, altering both deflection and survival. The particle's path and its identity co-evolve, and the simulation must track both. The result is a map of likelihood, not a pinpoint, and that shift is philosophical as well as technical, because it changes what counts as an answer. Some regions of the nearby universe become more plausible, while others fade without being fully excluded. The void may be unlikely, but it is not automatically impossible, and that distinction matters. Science often advances by replacing impossible with improbable, then measuring the difference. Bayesian mapping also forces honesty about priors, which are assumptions dressed in mathematics, and priors can quietly steer conclusions. If we assume sources follow galaxy density, voids start disfavored before any backtracking is done, because emptiness carries low prior weight. That is not bias in the moral sense, but it is a choice that must be stated aloud. The prior is a declaration of what we think the universe tends to do, yet priors can mislead if the true sources are rare or transient, because rarity breaks the link to ordinary structure and ordinary catalogues. A single extreme event might come from an object class that does not trace ordinary galaxies in a smooth way. It might be a brief flare, a hidden jet, or a source that is bright in particles but dim in light. If so, the void could be a blind spot in our electromagnetic expectations, not in reality. So the inference becomes a negotiation between physics and ignorance, and the negotiation is the honest heart of the chapter, because it admits what we do not know. Magnetic fields, composition, and source catalogues all enter as uncertain inputs, and each uncertainty broadens the cloud. Each new measurement has the potential to tighten it, but only if it is tied to the right physical lever. The field is learning which levers matter most. Amateros therefore deepened the mystery rather than resolving it, which is often what the best data do when they arrive at the edge of knowledge. It added a new data point, but it also highlighted how little a single direction can mean. The event is a beacon, yet the beacon shines through fog. The fog is not metaphorical, it is magnetic and statistical. The event also reopened the tension between local structure and local emptiness, and it did so with renewed force that is hard to ignore. The GZK horizon pushes sources nearby, yet the best fit backtrack points toward a void, as if the universe is teasing us. The universe seems to insist on proximity, while the sky seems to gesture toward absence. Which insistence should we trust more, the physics of losses or the geometry of arrival? That mismatch is the chapter's central unease, and it is not easily dismissed by a clever plot or a single recalibration. Either the void hides a capable engine, or our reconstruction is being bent by unseen magnetism, or our composition guesses wrong. Either way, the story is not about one particle, but about how we interpret a sparse set of extreme messengers. The menagerie is small, but it forces large revisions. Agassa's 1993 event marked the moment the anomaly became a menagerie, a small collection rather than a solitary specimen, and collections change what questions are reasonable. Amaterasu showed the menagerie still lives, and it still refuses to be catalogued, even with modern instruments. The extremes are not a single myth, but a recurring challenge. They return often enough to demand a method, not a miracle. To move forward, the story must shift from where these particles come from to how we read them. Direction alone is not enough when charge scrambles the sky, and the scrambling is energy dependent, which makes naive pointing deceptive. Energy alone is not enough when systematics shift the scale, and the scale determines whether an event is ordinary or forbidden. We need a third axis of evidence, something that speaks to identity. Composition becomes the missing key because it sets rigidity, deflection, and the meaning of backtracking, and it does so with multiplicative power. It also sets how the particle interacts with background light, and therefore how far it can plausibly travel before it is degraded. In a universe full of photons and fields, identity is destiny. If we can learn the identity, we can begin to read the root. That brings us to the next practical question, and it is as concrete as it is profound. How do we detect an invisible primary, and how do air showers encode both energy and composition? The answer is not hidden in the sky, but written in the cascade that the sky creates. The atmosphere becomes a detector medium, and the shower becomes a diagnostic object. The answer is written in the shower's development, which is a fast, violent chain reaction in thin air, unfolding over tens of kilometers in altitude. It is written in where it peaks, how many muons it makes, and how its footprint spreads across the ground. Those features are not decorative because they depend on the first interaction and the particle's mass. The first collision is the opening move, and everything after is a consequence. A lighter primary tends to penetrate deeper before producing its maximum, while a heavier nucleus tends to interact earlier and develop sooner because it behaves like many nucleons arriving together. The depth of maximum is called Xmax, and it is measured in grams per square centimetre, which is a way of counting air rather than meters. In plain terms, it tells us how far into the atmosphere the cascade reaches its brightest moment. It is one of the clearest composition handles we have. Xmax is not a single number with a single meaning, because fluctuations matter as much as averages. Proton showers fluctuate more from event to event because the first interaction point varies widely, while heavy nuclei average out variability across many nucleons, so the width of the Xmax distribution becomes evidence, not just the mean. The atmosphere is noisy, but the noise itself carries information. Muon content is another clue, because muons trace hadronic activity in the shower, and hadrons are where composition hides. More muons generally indicate a heavier primary or different interaction physics, and the distinction is part of the current tension in the field. On the ground, muons arrive with a certain time structure, and that structure can reveal how the shower evolved above. Muons are stubborn particles, and their stubbornness makes them useful. The lateral spread of particles across the surface also carries information, because geometry records the shower's altitude history. A shower that develops higher has more time to spread, and its footprint becomes broader, with a softer fall-off. A shower that develops deeper can be more compact, with sharper gradients in particle density. Even the curvature of the shower front can encode how far the cascade travelled before it reached the array. If we can measure those signatures reliably, we can narrow the charge, even if we cannot name the nucleus with certainty, and narrowing is enough to change the backtracking game. If we can narrow the charge, we can narrow the magnetic uncertainty, because rigidity stops being a wild guess. The backtracking cloud shrinks as composition becomes less ambiguous. The void either becomes more plausible, or it fades into a magnetic artifact. And if we can narrow the magnetic uncertainty, the sky can begin to point again, at least statistically. And statistics is how cosmic ray astronomy must begin. The central question remains, but the method must become more disciplined, and the instruments must become more self-aware about their own assumptions. The menagerie will not be tamed by a single spectacular event, but by a consistent reading of many. The story will be written in distributions, not anecdotes. The universe is sending messages at energies that strain our limits, and it sends them without explanation, as if daring us to decode them. To read the return address, we must first learn the language of the cascade, including its timing, its light, and its muons. Only then can the void, the filaments, and the candidate engines be judged on equal terms. Only then can the menagerie of extremes become a map rather than a mystery. The atmosphere is our laboratory, because the primary cosmic ray almost never reaches our instruments intact. At ultra-high energy, the first collision happens far above the ground, often higher than commercial flight paths, and the original particle is effectively erased. What we detect instead is a fast-evolving cascade, written into air, light, radio, and ground signals. In practice, the sky becomes both target and detector, and the experiment begins before any electronics can even decide to look. Visually, it begins as nothing more than emptiness, a dark sky over a quiet array, with only stars and a thin, layered atmosphere. You can almost imagine the air as stacked sheets of density, fading from near vacuum to the heavy lower troposphere. Then, without warning, an invisible projectile arrives at nearly the speed of light, carrying energy that would be absurd in any human-made beamline. In a fraction of a microsecond, the sky becomes a transient particle detector, and the air itself becomes the recording medium. The event leaves no scorch mark, yet it briefly reorganizes a column of atmosphere into a measurable, structured phenomenon. A primary cosmic ray enters as a proton, or as a heavier nucleus, already bent and scrambled by magnetic fields during its long journey. Even before it reaches Earth, it has been deflected by the interstellar and intergalactic magnetic web, an invisible lens that depends on charge and rigidity. Rigidity is the quiet variable here, momentum per unit charge, and it determines how stubbornly a particle holds its line. By the time it meets our planet, its direction may already be a compromise between where it came from and what it passed through. That compromise is why arrival directions are clues, not fingerprints, especially when the primary is a high-charged nucleus. It meets the upper atmosphere where nitrogen and oxygen nuclei become the target material, and where the air is thin enough that the first interaction point can vary widely. The encounter is a hadronic collision at a centre of mass energy beyond human accelerators, because the target nucleus is effectively at rest, while the incoming particle is ultra-relativistic. Nature runs a particle physics experiment at scales the LHC cannot touch, and it does so with no warning, no trigger button, and no second chance. The first interaction depth is a random draw from an exponential probability set by the interaction cross-section, and that randomness echoes through the entire shower. To make that comparison concrete, the LHC reaches centre of mass energies of 14 tera, electron volts in proton-proton collisions. A single cosmic ray proton of about 10-20 electron volts colliding with a stationary air nucleus reaches a centre of mass energy of hundreds of tera, electron volts, an order of magnitude beyond the collider frontier. That gap matters because the shower we observe depends on cross-sections, multiplicities, and energy flow in a regime where we must extrapolate. Even small changes in inelasticity, the fraction of energy dumped into secondaries, can shift where the shower brightens and where it fades. The first impact produces secondary hadrons, dominated by pions and kaons, plus baryon fragments that carry the memory of the original projectile. In the language of particle physics, the collision is inelastic, and a large fraction of the incoming energy is converted into new particles. Some fragments continue forward in a leading direction, while others spray sideways with transverse momentum that later becomes the shower's lateral spread. That sideways kick is modest in particle terms, yet it becomes kilometres of footprint by the time the cascade reaches the ground. Neutral pions decay almost immediately into gamma rays, and that near-instant decay is one of the cascade's key turning points. The gamma rays seed an electromagnetic subshower through pair production, creating electrons and positrons that radiate more photons by bremsstrahlung. In this branch, energy is repeatedly split, and the number of particles multiplies rapidly while individual energies drop. The process has a rhythm: photon to pair, pair to photon, and back again, until the air's ionization losses finally dominate. By then, the shower has become a moving swarm, with the electromagnetic component carrying much of the visible energy deposition. Charged pions and kaons face a competition between interaction and decay, and the atmosphere decides the outcome. At high energy, they tend to interact again before decaying, feeding the hadronic core and generating more secondaries. As energies fall, decay begins to win, and the shower starts producing muons and neutrinos in earnest. The balance depends on air density and path length, so a steep shower and a grazing shower can produce different muon outcomes, even at the same primary energy. Muons are born mostly from pion and kaon decay, and they are the shower's long-distance messengers. They're heavier than electrons by a factor of about 200, so they radiate less and lose energy more slowly. Many muons therefore survive the trip to the ground, arriving as a penetrating component that can pass through meters of material. Their long lifetime is also stretched by relativity, so a muon created high above can still arrive intact, like a delayed telegram from an earlier stage of the cascade. When you stand at a detector, muons are often the first clear sign that the hadronic backbone was strong. Neutrinos also emerge from these decays, but they almost never interact in the air column above an array. They carry away invisible energy, energy that does not contribute to fluorescence light or to most surface signals. That missing fraction is small but not negligible, and correcting for it is part of what makes air shower reconstruction a careful accounting exercise. The correction is also a reminder that the shower is not closed, because some energy simply leaves the scene without a trace. In a sense, every reconstructed energy is an estimate of what stayed behind, plus a model-based guess of what escaped. With each generation, particle number multiplies while average energy per particle drops, and the cascade becomes an extensive air shower spreading laterally as it grows downward. The shower front is thin in time, often tens of nanoseconds at a given point, yet it can be kilometers wide on the ground. The atmosphere acts like a calorimeter, but it is a calorimeter we can only sample, and we must do so through imperfect windows. Those windows include ultraviolet photons, radio pulses, and the final rain of particles, each filtered by geometry and by weather. A useful mental image is a luminous pancake moving downward at nearly light speed, slightly curved, with a dense core and a thinning edge. Near the axis, particle densities are high and signals saturate quickly, while farther out the shower becomes sparse, and timing becomes the dominant clue. The footprint is not a simple circle either, because geometry, geomagnetic effects and shower age shape it into asymmetric patterns. At large zenith angles, the footprint stretches into an ellipse, and the electromagnetic component can be partly absorbed before it ever reaches the ground. The key diagnostic is longitudinal development, the rise and fall of particle number with depth as the shower evolves. Depth is measured in grams per square centimetre, counting air mass rather than altitude, because what matters is how much material the cascade has traversed. A given depth corresponds to different altitudes depending on weather and season, which is why atmospheric monitoring becomes part of the experiment. Pressure profiles, temperature layers, and aerosol content quietly alter the conversion between what we see and what actually happened. The atmosphere is not just a stage, it is a variable instrument component. The shower reaches a peak called X max, then attenuates as energy is dissipated into ionization, excitation, and low-energy secondaries. X max is not just geometry, it is a clue to the primary's mass because different primaries start their multiplication at different depths. It is also a clue to the interaction physics, because the first few collisions set the pace for everything that follows. When X max shifts with energy, it can signal changing composition, or it can signal that our extrapolated hadronic models are missing something important. Proton showers tend to penetrate deeper before reaching X max, because a single nucleon starts the chain, and must first produce enough secondaries to build the cascade. Heavy nuclei behave like many nucleons arriving together, so they interact earlier and develop sooner, an idea often summarized by the superposition picture. In that approximation, an iron nucleus behaves like 56 lower energy nucleons arriving in a tight bundle. The picture is imperfect, yet it captures the intuition that many smaller starts build a shower earlier than one big start. The average X max shifts upward in the atmosphere for heavier primaries at fixed energy, and the shift is large enough to measure statistically. Fluctuations also differ, with protons showing larger event-to-event spread because the first interaction point and early multiplicities vary more. Heavy nuclei average over many nucleons, so their showers are typically more stable in depth, even when the energy is the same. That stability becomes a signature when you collect enough events to see distributions, not just individual tracks. Muon content adds another lever because muons trace the hadronic backbone that fluorescence light only hints at indirectly. More hadronic energy typically means more muons at ground, and heavy primaries often produce more because their early interactions distribute energy into many hadronic branches. Muons also arrive with different time structure than the electromagnetic component, often earlier in the shower front's leading edge. Their angular spread is narrower too, so they preserve more of the shower axis information as they propagate. That timing difference is not just a curiosity, because it encodes where in the atmosphere the particles were produced. Electromagnetic particles scatter and multiply, so their arrival times broaden, while muons travel straighter and keep a tighter temporal signature. Measuring muons therefore tests both composition and the hadronic models extrapolated beyond accelerators, and it exposes where those models might be incomplete. If the muon count is persistently high compared with predictions, the discrepancy becomes a pressure point on the theory, not merely a nuisance for reconstruction. This is why detectors rarely claim to see the original particle directly, even when the reconstruction is exquisite. The primary is gone after the first interaction, and the first interaction is hidden in thin air, beyond the reach of any direct instrument. We infer the primary's energy, direction, and mass from patterns in the secondary cascade. The entire field is an inverse problem built on a transient atmospheric event. It is like reconstructing a stone's shape from ripples on a pond, except the pond is three-dimensional and the ripples are particles. That inverse problem has a particular tension at the highest energies, because the events are rare and the uncertainties are layered. A single shower carries information, but it also carries ambiguity, and the experiment must learn to separate the two. The goal is not merely to detect a shower, but to decode it, using physics as a translation key. Every decoding step has an error bar, and at the top of the spectrum those error bars can decide whether a feature is real. Air shower physics has deep roots that predate the modern ultra-high energy hunt, and those roots shaped how we think about cosmic rays today. In 1933, Bruno Rossi used coincidence techniques to reveal correlated particles and cosmic ray events, showing that detections separated in space and time could belong to the same phenomenon. His work helped establish that cosmic rays were not just isolated hits, but structured events with internal relationships. It also helped drive the idea that timing, not just counting, could reveal hidden structure in what looked like random noise. In 1937, Pierre Auger and collaborators recognized extensive air showers spanning large areas, using detectors separated by hundreds of meters. Their insight turned the sky into a source of giant cascades and the ground into a detection plane that could be scaled. It was a conceptual leap. If the shower is huge, then the detector can be huge too, and the rarity of the primaries can be met with area. That early work also foreshadowed modern arrays, where separation distances and coincidence windows become design parameters, not afterthoughts. There is a historical irony in that early work because the atmosphere was first seen as an obstacle, something that blocked and altered the primaries. Then it became a tool, a natural amplifier that turned one particle into billions, making the invisible detectable. The same air that destroys the primary also makes the measurement possible, an act of erasure that doubles as a method. The field learned to treat the atmosphere as an active medium, not an inconvenient layer between space and our instruments. Modern observatories scale that early logic into continental instruments, designed around the brutal statistics of ultra-high energy events. They combine optical telescopes that watch the shower's growth with surface arrays that sample its footprint, and increasingly, with radio antennas that listen for coherent pulses. Each technique measures different features, and each carries different systematics, which is why the combination matters. The design philosophy is pragmatic. When nature gives you only a few events, you extract every possible observable. The point is not redundancy for its own sake, but cross-checks that survive rare statistics and shifting atmospheric conditions. When events are scarce, a single systematic bias can masquerade as a discovery, and a single calibration error can tilt an entire spectrum. Multiple views of the same shower create constraints that are hard to fake. They also create internal alarms, because inconsistencies reveal when the atmosphere, the electronics, or the models have drifted. Fluorescence detection follows the fly's eye lineage through Hires and the telescope array, and it remains one of the most direct ways to watch a shower develop. Charged shower particles excite atmospheric nitrogen, which then emits ultraviolet fluorescence as it relaxes back to its ground state. The light is nearly isotropic, so a telescope can see a track even when it is off-axis, like a faint chalk line drawn across the night. The glow is dim enough that the stars remain visible, and that contrast makes the shower feel both delicate and immense. The track is faint, and the atmosphere itself is both the source and the filter, which makes the measurement feel like astronomy and laboratory physics at once. Photons must survive scattering by molecules and aerosols, and they must pass through a variable column of air whose clarity changes with humidity, dust, and wind. For the analyst, every shower is also an atmospheric measurement, whether they want it to be or not. Even the clear nights are not identical, so calibrated light sources and atmospheric profiles become part of the data. Fluorescence is close to calorimetric because light yield tracks energy deposited by ionization, and ionization is where the cascade spends most of its energy. By integrating the light along the shower path, analysts estimate the electromagnetic energy in the cascade, essentially reading the shower's energy ledger as it is paid into the air. They then correct for invisible energy carried by neutrinos and penetrating muons, which do not fully contribute to the fluorescent signal. The result is a measurement that feels direct, yet it still carries a subtle dependence on what the hadronic channel did upstream. The correction depends on interaction models and composition assumptions, so even calorimetry is not model-free, especially at the highest energies. If the hadronic physics changes, the invisible fraction can change, and the energy scale shifts subtly, but meaningfully. That sensitivity is one reason airshower experiments are also, unavoidably, experiments in particle physics. The sky is delivering collisions at energies we cannot tune, so the data become both astrophysical evidence and a stress test of our extrapolations. Geometry comes from timing and the changing angle of the track across the camera, because the shower appears to move across the field of view as it descends. A single telescope can reconstruct a shower detector plane, but distance along that plane can be degenerate, especially when the observed track is short. Brightness profile and timing help, yet monocular events can carry larger uncertainties, and those uncertainties propagate into energy and X-max. The reconstruction is therefore a careful fit, balancing what the camera saw against what the shower could physically be. Stereo viewing or hybrid constraints tighten the axis and reduce ambiguity, because intersecting lines of sight pin down the trajectory in 3 dimensions. When 2 telescopes see the same shower, the geometry becomes a triangulation problem rather than a guess. When a surface array also times the front, the shower's path becomes a locked solution rather than a floating one. In visual terms, the shower stops being a streak on a dome and becomes a line in space with a measurable distance scale. Fluorescence has a hard operational limit because it needs dark, clear skies, and the night is not always cooperative. Moonlight raises background and washes out the ultraviolet signal, turning a clean track into a noisy smear. Clouds and aerosols scatter and absorb light, biasing energy unless monitored continuously with lasers, lidars, and calibrated light sources. Even thin cloud layers can clip the profile, hiding the true X-max and leaving analysts with a partial story. The duty cycle is low, roughly 13 to 15%, so exposure grows slowly even when the instrument is working perfectly. That limitation shapes the entire observational strategy because it forces a trade between depth information and event count. In practice, fluorescence gives exquisite individual events, while surface arrays provide the statistical backbone. The field lives with that compromise because the physics demands both detail and volume. Surface arrays answer that limitation with near-continuous operation, and they do so with a different philosophy of measurement. They do not need darkness, and they tolerate ordinary weather because they measure particles at ground rather than light in the air. They sample the shower front when it reaches the ground, measuring particle densities and arrival times across a wide area. Each station is a local witness, but the array is the real instrument, because the pattern across many stations is the message. The array trades direct longitudinal viewing for statistics and uptime, and that trade is deliberate. A surface station is a simple witness. It reports when the front arrived, how large the signal was, and how it evolved over tens to hundreds of nanoseconds. When hundreds or thousands of stations speak together, the shower's geometry emerges from their collective timing. The reconstruction is like listening to thunder with many microphones, using delays to infer where the lightning actually struck. The Pierre Auger Observatory in Argentina is the flagship surface array at the highest energies, built for the extreme rarity of trans-GZK events. It covers about 3,000 square kilometers, a landscape-scale instrument laid out with regular spacing, where each station is both autonomous and synchronized. The scale turns decades of waiting into a manageable observational program, because area is the currency that buys exposure. At the highest energies, the universe does not give you many chances, so the array must be ready every minute. In a wide aerial view, the array looks like a geometric grid stitched onto the pampas, with mountains on the horizon and a sky that seems too large for any human project. Each station sits quietly, powered and calibrated, watching for a signal that may come only a few times per year at the very top of the spectrum. The silence is part of the design, because the events are rare and the background must be stable. When a shower arrives, that silence breaks into a brief coordinated burst of timestamps and waveforms. A surface array reconstructs direction by timing triangulation across many stations, using the fact that the shower front arrives as a tilted plane. The relative trigger times define the plane's normal, and therefore the incoming direction, with corrections for curvature and thickness. Curvature and thickness of the front add refinements at large zenith angles, where the shower has travelled through more atmosphere and the front spreads out. Those refinements matter, because a few nanoseconds of timing error can translate into a meaningful angular shift on the sky. The result is an arrival direction that can be precise even when composition is uncertain, because timing is a geometric measurement first. Yet even here, physics intrudes, because different primaries and different shower ages can alter the front's shape and particle content. Reconstruction therefore blends geometry with informed modelling, and the best solutions use both. The array is measuring not just when something arrived, but what kind of front that something was. Energy inference comes from the lateral distribution of signals around the shower core, the point where the axis intersects the ground. Analysts fit how signal strength falls with distance, then evaluate a reference signal at a standard radius, chosen to reduce sensitivity to fluctuations. That reference correlates with primary energy, but the mapping depends on simulations and on how the shower develops in the atmosphere. The atmosphere again becomes part of the calibration, because density profiles affect how much of the electromagnetic component survives to ground. Hadronic interaction models and composition assumptions therefore enter the surface energy scale, even when the detector response is perfectly calibrated. If a model predicts too few muons, the same ground signal might be interpreted as a different energy or as a different mass than reality. This is why surface arrays are powerful, but also why they benefit so strongly from hybrid calibration. The goal is to keep the energy scale anchored to something closer to calorimetry, while still exploiting the array's enormous exposure. Cherenkov detection in water is the core physical mechanism in Auger's tanks, and it is elegant in its simplicity. When a charged particle moves through water faster than light's phase velocity in that medium, it emits Cherenkov radiation. The light forms a directional shock wave, like an optical cone trailing the particle, and the cone angle encodes the particle's speed relative to the medium. In the tank, that cone bounces and diffuses, turning a brief passage into a measurable flash. It is important to say what faster than light means here, because no physical law is broken. Light travels more slowly in water than in vacuum, so a particle can outrun the local light wavefront while still moving below the universal speed limit. The result is a prompt, bluish flash that is brief but information-rich. In visual terms, it is like a miniature sonic boom made of photons, produced inside a sealed, darkened volume. Photomultiplier tubes convert the light into electrical pulses that can be timed and integrated, turning photons into waveforms. The waveform is not just a count because its shape carries clues about what passed through the tank. Calibration often uses the signal of a single vertical muon as a reference. Because muons are abundant and their response is stable, that reference becomes a common language across thousands of stations, allowing the array to behave like one coherent instrument. The Cherenkov signal is a mixture of electromagnetic particles and muons, and the mixture changes with distance from the core and with shower age. Muons leave long penetrating tracks that produce characteristic pulses, often sharper and more isolated. Electrons and photons create shorter cascades that spread light differently, producing broader, more complex waveforms. Far from the core, where the electromagnetic component thins out, muons can dominate, and the tank's waveform becomes a kind of muon counter in disguise. Separating these components is difficult, yet it is central to composition inference, because muon richness is tied to the hadronic channel. Analysts use timing, signal shape, and sometimes dedicated hardware upgrades to improve that separation. Each improvement is a step toward reading not just the shower's size, but its internal anatomy. The ambition is to turn a simple water tank into a diagnostic instrument, sensitive to the balance of branches in the cascade. No single method is sufficient at the energies that matter for the source mystery, because each method sees only part of the event. Fluorescence sees the longitudinal profile and X-max, but it is limited by duty cycle and atmospheric transparency. Surface arrays see huge exposure and stable timing, but energy and composition depend on models, and those models are stretched. The most reliable picture emerges when the same shower is forced to agree with multiple measurement channels. The solution is to combine them in a hybrid strategy, so that the weaknesses of one become the constraints of the other. Hybrid detection uses fluorescence to anchor the energy scale and shower development, because calorimetric information is hard to fake. It uses surface timing to lock down geometry and core location with many clocks, because timing is robust and continuous. When the two systems agree, the event becomes more than a detection, it becomes a calibrated physical object. When both systems observe the same event, degeneracies collapse, and the shower becomes a solved object rather than a partially inferred one. Systematic uncertainties shrink because each method constrains the other's weak points, and because the same shower is forced to satisfy two different measurement languages. In a field where statistics are precious, that kind of cross-validation is a form of insurance. It also builds confidence in long-term trends, because the calibration is repeatedly tested against real showers. Auger's hybrid design made this philosophy operational at scale, and it did so with a careful layout. Fluorescence telescopes ring the array, watching the same air volume the tanks sample at ground, so that a shower can be seen both in flight and at impact. Hybrid events calibrate the surface energy estimator against a calorimetric measurement, tying the array's continuous data stream to a more direct energy scale. Over years, that linkage becomes a backbone for the spectrum, not just a technical detail. Over time, this cross-calibration stabilizes the spectrum and reduces experiment-to-experiment tension, because the energy scale becomes anchored in a shared physical basis. It also reveals where models struggle, because discrepancies appear as patterns rather than as isolated anomalies. The hybrid approach therefore improves measurement, and it improves interpretation. When different observables disagree in a consistent way, The disagreement itself becomes a result. Hybrid data also sharpen composition studies because X-max and ground muons can be compared event by event, not just in separate distributions. If models predict a certain muon content for a given X-max and energy, the detectors can test it under real atmospheric conditions. Persistent muon discrepancies become evidence that hadronic physics at extreme energies may be incomplete, and that our extrapolations may be too simple. The question becomes unavoidable. Are we misreading the primaries, or are the collisions themselves behaving differently than expected? In that moment, the atmosphere becomes a laboratory, not only for astrophysics, but for particle interactions, because the data are probing the rules themselves. Are cross-sections rising as expected, or faster? Are multiplicities and inelasticities distributing energy differently than our tuned models assume? Each shower is a message from a regime we cannot reproduce on Earth, and each message must be decoded carefully. The suspense is quiet, but it is real, because it sits at the boundary between known physics and possible surprises. A third technique is now joining the toolkit, driven by radio detection, and it fits naturally into the multi-instrument philosophy. Air showers produce coherent radio pulses as they develop, especially in the tens of megahertz band, and those pulses are fast enough to demand precise electronics. The dominant mechanism is geomagnetic, where electrons and positrons are separated by Earth's magnetic field, creating a transverse current that changes rapidly with time. That current is strongest when the shower is young and dense, so the radio signal carries an imprint of where the shower's energy was concentrated. The time-varying transverse current emits a short broadband pulse, and its polarization is tied to the geomagnetic geometry. That link is valuable because it provides an internal consistency check. The signal should point the way the physics says it should. When it does, confidence grows that the pulse is truly from a shower, not from human interference. In visuals, the antennas see a brief needle-like waveform, synchronized across the array like a wink traveling over the ground. A second contribution comes from the Askaryan effect, a net negative charge excess in the shower front that develops as electrons are knocked free from air molecules. That charge imbalance also changes with time as the shower grows and fades, and it contributes a radio component with its own polarization pattern. The observed pulse is therefore a superposition, and careful analysis can separate the ingredients. When both components are measured cleanly, the radio signal becomes not just a trigger, but a diagnostic of shower geometry and development. Coherence makes the signal scale strongly with shower energy, because the wavelengths are long compared to the shower front thickness. When many charges radiate in phase, the electric field grows roughly with particle number, and the received power grows even faster. Radio therefore offers an energy proxy that can be competitive with optical methods, especially when calibrated against hybrid events. It also offers a different kind of calorimetry, because the field strength is tied to the electromagnetic component's collective motion. Radio arrays typically target about 30 to 80 megahertz to avoid strong broadcast interference, and to sit in a band where the atmosphere is relatively transparent. Antennas sample the pulse shape, polarization, and lateral footprint, capturing a two-dimensional pattern on the ground. The footprint size and asymmetry carry information about shower development and X-max, because the emission region and viewing geometry imprint themselves onto the pattern. The pattern is not arbitrary, it is a projection of a moving current system, and it can be modeled with increasing precision. Polarization encodes the geomagnetic direction, offering a built-in consistency check that is both physical and practical. If the polarization is wrong, the event may be contaminated or misreconstructed. If it is right, the event becomes a trustworthy probe of the shower's electromagnetic evolution. That simple vector direction, measured in the field, becomes a signature of an invisible cascade overhead. Radio detection also predicts a distinctive late-time component, sometimes called a sudden death signal, tied to the shower's abrupt termination at the ground. When the shower front hits the surface and the collective charge motion stops abruptly, an additional pulse can be produced, like the final note of an instrument being muted. Detecting it is challenging, because it is weak and can be confused with local noise, yet it could help constrain the shower's end stage. If measured reliably, it would add another timing marker, one more anchor point in the shower's fleeting timeline. It is another way to turn the ground impact into information rather than loss, and it fits the broader theme of air shower work. The primary is gone, and the shower is fleeting, so every secondary signature becomes valuable. The more independent observables we can measure, the more tightly we can constrain the invisible cause. In a field built on inference, additional constraints are not luxuries, they are survival tools. Radio has practical advantages that address fluorescence weaknesses, and those advantages are not merely logistical. It can operate in daylight and does not require moonless nights, so its duty cycle can be far higher. It is less affected by aerosols and optical scattering, though thunderstorms and atmospheric electricity can complicate data and even create their own radio transients. That complication is itself a reminder that the atmosphere is alive with processes, and the experiment must distinguish cosmic signals from terrestrial ones. With careful filtering and site selection, radio can expand duty cycle while still probing longitudinal development, especially when combined with other instruments. In the best case, radio becomes a bridge between the continuous coverage of surface arrays and the profile sensitivity of fluorescence. It adds a third perspective with different systematics and different vulnerabilities. When three methods converge on one shower's story, the reconstruction becomes harder to doubt. The emerging picture is a multi-instrument approach to an invisible primary built from complementary measurements rather than a single perfect detector. Fluorescence gives a near calorimetric energy and a direct X-max handle, but it asks for darkness and atmospheric clarity. Surface arrays give exposure, direction, and muon-rich sampling of the hadronic component, but they lean on models for interpretation. Radio adds high duty cycle sensitivity to shower development and geometry, with different atmospheric systematics, and with polarization as a built-in physics check. Together, these methods turn a single air shower into a multi-channel dataset, where each channel tells part of the story. The art is to make the parts agree, and to understand what it means when they do not. Disagreement can be a warning about calibration, yet it can also be a hint that the underlying physics is shifting with energy. That ambiguity is part of the chapter's mystery, because the data are both measurement and message. Each method is a different cut through the same physical object, like taking slices through a moving, evolving structure. Energy is inferred from deposited ionization, ground signal size, and coherent emission strength, each linked to different parts of the cascade. Geometry is inferred from light track timing, station triangulation, and radio wave fronts, each with its own precision and failure modes. Composition is inferred from X-max distributions, muon content, and correlations between longitudinal and ground observables, because no single observable is decisive. A proton shower can sometimes look heavy, and a heavy shower can sometimes look light, especially when fluctuations are large. Only by building populations and cross-checking observables can the experiment separate trends from chance. Even then, the conclusions are often probabilistic, not absolute, because nature does not label the primaries for us. The question is not, what was this one particle? But what population is the sky sending at this energy? The deeper reason this matters is that composition controls the entire source problem, even when the sky map looks tempting. Charge sets magnetic deflection, so it sets whether directions can ever point back to sources with meaningful accuracy. A proton at the highest energies might preserve some directional memory, while an iron nucleus could be bent enough to erase it. When we ask whether the universe has point sources at these energies, we're also asking what the primaries are made of. Mass and energy per nucleon set propagation losses, so they set the GZK horizon differently for nuclei, and they shape what nearby means at extreme energy. A nucleus can photodisintegrate, shedding nucleons and changing identity mid-flight, which complicates any attempt to trace it backward. Without composition, every sky map is a blurred overlay of incompatible trajectories, and every correlation can be both true and misleading. The return address is written in the data, but the ink is smeared by charge and by interactions along the way. There is also a second reason that is easy to miss because it hides inside the reconstruction itself. The first interaction is at energies beyond accelerators, so shower measurements test hadronic physics in a new regime where we do not have direct calibration. If interaction cross-sections, multiplicities, or inelasticities differ from extrapolations, then energy and composition inference shifts, sometimes in the same direction. A model that underestimates muons, for example, can make primaries appear heavier, even if the sky is not changing at all. The detectors are not only reading the universe, they are checking the rules used to read it, and that is a subtle kind of suspense. When a muon excess persists, is it telling us about heavier primaries or about new interaction behavior? When X-max trends shift, is it composition changing, or the physics of the first collisions evolving with energy. The data force us to ask which assumptions are safe. They also force us to admit that unknown systematics is not a placeholder. It is a real possibility at the frontier. This chapter's laboratory is therefore not a building, but a column of air above the array, measured in mass and time. A single primary triggers a chain reaction, and the chain reaction is what we can measure in photons, radio pulses, and tank wave forms. The art is to extract the primary's identity from the cascade's geometry and particle content, while admitting what remains uncertain. In the end, the atmosphere gives us a record, but it is a record written in a language we are still learning to translate. The reward is a cleaner handle on the return address problem, the question of where these particles came from and what happened along the way. Each improvement in calibration and each reduction in systematic uncertainty narrows the list of plausible origins. Each better composition constraint makes magnetic deflection less of a fog and more of a calculable distortion. The mystery does not vanish, but it becomes sharper, and sharper mysteries are the ones science can actually solve. Once we can measure energy and composition reliably, the next question becomes unavoidable, and it arrives with a kind of quiet force. What could accelerate anything to these energies in the first place, and what environments can hold such fields without tearing themselves apart? The story turns from detection to engines, and the hunt for Zevatrons begins. Once we can measure energy and composition reliably, the next question becomes unavoidable. What kind of engine can push a single charged particle toward a zepter electron volt without cheating the basic rules of electrodynamics? A zepter electron volt is not just a bigger number on a graph, and it is not merely a bragging rights milestone. It is a scale where a single particle carries macroscopic punch, like a thrown baseball compressed into a subatomic speck, but with its momentum packed into one charged point. At that energy, the particle's Lorentz factor is so extreme that time, in its own frame, barely moves at all. When detectors reconstruct such an event, the implication is immediate and unsettling. Somewhere, nature is building accelerators beyond anything humans can engineer. Physicists use a blunt new word for that engine, because ordinary labels start to feel inadequate under the weight of the numbers. A Zevatron is any astrophysical accelerator that can plausibly reach ZeV energies, at least for some charge and some set of conditions. The term is modern slang with an old motivation. When the data forces you to name the missing machine, vocabulary becomes a tool of survival. Oh my god, class events force the vocabulary into serious discussion, because they are too energetic to ignore politely. They are not just rare points on a spectrum, and they are not merely statistical curiosities at the edge of exposure time. They are demands for an energy source, and they press on every assumption about what cosmic environments can actually do. If the universe can launch one such particle, what else is it doing in the dark between galaxies? At these energies, acceleration is not only about power, and it is not only about having a dramatic object on a poster. It is about confinement, time, and escape, three constraints that pull in different directions and rarely align cleanly. A particle must be held long enough to be boosted, yet it must also leave before losses shave away the energy it just gained. The engine must be strong, but it must also be gentle in exactly the right way. The first suspect filter is simple and cruel, and it arrives before any detailed plasma modelling can offer comfort. It comes from A.M. Hillis, who asked what objects can even hold the particle in the first place. His question was geometric, almost embarrassingly practical. If you cannot keep the particle inside the machine does not exist. In the late 20th century, that practicality became a kind of discipline for the field. The Hillis criterion starts with the gyro radius, the circle a charged particle wants to trace in a magnetic field. In plain terms, magnetism bends the path, and the particle's momentum fights that bend with stubborn inertia. If the orbit is larger than the source, the particle leaks out, and the acceleration attempt ends as a simple escape. At ZeV energies, that orbit can swell to astrophysical scales, which is why the criterion bites so hard. You can picture it visually as a spark trying to spiral inside a magnetic bottle, and the bottle is made of invisible field lines. If the bottle is too small, the spiral clips the wall and the spark is gone into space. Confinement is the hard gatekeeper because it is geometric, and geometry does not negotiate with optimism. Even the most sophisticated microphysics cannot rescue a source that is simply too small. Hill has turned that intuition into a maximum energy estimate, and the elegance is part of its power. The limit scales with magnetic field strength times size times a speed factor, times particle charge, with order unity details depending on the exact acceleration geometry. It is not a full theory of acceleration, but it is a ruthless first cut that clears the table. It tells you which dreams are dead on arrival. In compressed form, the rule is rigidity versus magnet size, and rigidity is the real currency at the top end. Rigidity is momentum per unit charge, and it controls how stubbornly a particle resists magnetic bending in any environment. Higher charge helps because it tightens the orbit, while higher energy hurts because it widens the orbit and pushes the particle toward the boundary. This is why composition is never a side detail in ultra-high energy cosmic rays. The speed factor matters because acceleration is not instantaneous, even in violent astrophysical flows with relativistic motion. Shocks and moving magnetic structures do work over many cycles, and each cycle takes time in a turbulent medium. Slow cycles lose to escape, and escape is always waiting at the edge of the source. A zevatron is not only a strong magnet, it is a clock that must run fast. The Hillis plot is a detective board, and it is drawn like a map of possibility with suspects pinned in place. Each candidate is placed by its size and magnetic field, and a diagonal line marks the minimum needed for a given energy. Only the points above the Zever line stay in the story. Everything below is eliminated without mercy. Visually, it feels like watching potential sources fall away into the margins. That filter does not prove anything can accelerate to Zev, and it never pretends to be a verdict. It only says which objects are not immediately impossible, which is a different and weaker claim. The hunt begins after the easy exclusions, when the remaining suspects still have to survive real physics. That is where the mystery becomes technical, and therefore sharper. Now the story shifts from geometry to mechanism. If an object can confine a particle, it still must transfer energy efficiently, and it must do so faster than nature can take it away. That transfer is the second gate, and it is where plasma processes become the deciding factor. The visuals shift too, from clean lines on a plot to restless, turbulent fields. Bottom-up acceleration is the conservative path, and it is conservative in the scientific sense rather than the emotional one. It starts with ordinary plasma physics and known astrophysical shocks, then tries to climb from thermal energies to the extreme tail. It assumes the universe builds its highest energies by repeated work, not by miraculous shortcuts. In other words, it assumes the cosmos pays its bills in installments. The workhorse mechanism is Fermi acceleration, named for Enrico Fermi's mid-20th century insight about stochastic gains. It is not one machine but a statistical process, and it relies on repeated encounters with moving magnetic structures. Particles gain energy by scattering off magnetic irregularities that act like drifting mirrors in a turbulent sea. The key is that the mirrors move, and motion is what turns random wandering into net gain. In the modern picture, diffusive shock acceleration dominates the discussion, because it is both simple and stubbornly effective. A collisionous shock forms in a plasma, meaning particles do not collide like gas molecules, yet collective electromagnetic forces still create a sharp transition. Magnetic turbulence on both sides scatters particles across the shock front, so the particle wanders back and forth instead of simply streaming away. The shock is a boundary, but it is also a pump. Each crossing is a bet with favourable odds, and the odds come from converging flows that do systematic work. In the shock frame, the upstream and downstream plasmas move toward each other, so a particle that bounces between them tends to gain a fraction of energy per cycle. The gain is small, but the process is persistent, like compounding interest applied to momentum over thousands of risky returns. The miracle is not the size of each gain, but the patience of the mechanism. The spectrum that emerges is a power law, which is one reason the mechanism is so beloved and so often invoked. Power laws appear naturally when each cycle has a fixed probability of escape, because the survivors form a scale-free tail. Much of cosmic ray data, across wide energy ranges, carries this signature, as if the universe prefers simple statistical rules. The mathematics feels almost indifferent, and that indifference is part of its credibility. Shocks work best where flows are fast and turbulence is strong, and where magnetic fields can be amplified beyond their quiet values. Supernova remnants do this well at lower energies, and observations of non-thermal X-rays show electrons being pushed to extreme speeds. Jets and winds extend the idea to larger scales, offering longer acceleration regions and repeated shock structures. Every time we see a shock-lit filament, we are seeing a potential energy ladder. At the very top end, the process strains in ways that are easy to state and hard to fix in practice. The acceleration time grows with energy because scattering becomes harder, and the particle needs larger coherent fields to turn around. When the gyroradius approaches the size of the shock region, the particle stops behaving like a trapped gambler and starts behaving like a traveller. The casino walls become irrelevant. The same turbulence that helps can also hurt, and the balance is delicate in extreme environments. If the magnetic irregularities are too weak, the particle streams out along nearly straight paths and the cycle count collapses. If they are too strong, losses can rise, and the environment becomes a radiative grinder rather than an accelerator. The zevatron must be turbulent, but not too turbulent in the wrong way. Losses are the silent enemy of every zevatron, and they come in more than one form with different signatures. A charged particle in strong magnetic fields radiates, and the radiation reaction can be severe at extreme energies. In dense photon fields it also interacts, and those interactions drain energy through particle production or nuclear breakup. Even empty-looking space can be crowded once you count every photon. Synchrotron losses are often summarized with a simple idea. Bend a charged particle hard enough, and it must pay in photons. Curvature radiation is the same tax paid along curved magnetic field lines, even when the particle is tied to the field rather than spiraling around it. At ZeV scales, even small curvatures can become expensive, because power rises steeply with energy. The particle is rich, and the universe is eager to collect. In bright environments, photons become targets, not just background light that politely illuminates the scene. Protons can undergo photopion production, effectively converting part of their energy into pions, and then into gamma rays and neutrinos. Heavy nuclei can be photodisintegrated, shedding nucleons like a ship losing rivets in a storm of ultraviolet and X-ray light. The very glow that makes a source visible can also make it hostile, so the bottom-up story becomes a three-way constraint that repeats like a refrain, because it never stops being relevant. Confinement must hold, acceleration must outrun losses, and escape must occur before the particle is degraded. A candidate that satisfies only one or two of these is not a zevatron, no matter how dramatic it looks in a telescope image. The universe does not award points for spectacle. With that framework, the suspects narrow to a few extreme environments, and the shortlist feels both exciting and troubling. They are rare, violent, and often distant, and they are also the places where plasma becomes exotic. The visuals shift accordingly, from tranquil star fields to jets, shocks, and magnetic structures drawn like luminous threads. The camera language becomes sharper, more kinetic, and more dangerous. First suspect is the active galactic nucleus, the bright heart of a galaxy powered by a supermassive black hole. Around the black hole, an accretion disk of hot plasma spirals inward, and magnetic fields twist and reconnect in a region that glows across the electromagnetic spectrum. In many cases, a relativistic jet punches outward, carving a narrow channel through interstellar and intergalactic gas. In long exposures, the jet looks like a needle of light sewn into the fabric of space. An AGN can act like a dynamo, converting gravitational and rotational energy into electromagnetic power with ruthless efficiency. Rotating plasma drags magnetic field lines, and the resulting stresses can extract energy from the disk and even from the black hole's spin. The jet carries that energy outward in ordered structures, sometimes remaining collimated over hundreds of thousands of light years. It is one of the few astrophysical systems that looks engineered, even though it is not. On a Hillis plot, AGN jets look promising for a simple reason. They are huge, and they stay huge for a long time. Their magnetic fields can be strong, their bulk speeds approach light speed, and their characteristic sizes dwarf most other astrophysical systems. If any object has room to hold a ZeV particle, a jet and its lobes are natural candidates. The geometry finally seems willing to cooperate. Shocks can form inside jets, where faster blobs catch slower ones, and at termination points where jets slam into external gas. Each shock is a potential Fermi engine, and each region offers repeated scattering in magnetized turbulence. In radio images, these sites appear as bright knots and hotspots, places where the jet's ordered flow breaks into chaotic dissipation. The jet is not a single river, but a chain of rapids. Relativistic motion helps in two ways, and both are subtle enough to matter at the margins where ZeV arguments live. It increases effective electric fields in the lab frame, because moving magnetic structures transform into electric components for an outside observer. It also reduces acceleration time in the jet frame for some processes, allowing more cycles before the particle escapes. At the top end, small factors are not small anymore, but AGN are not automatic Zevatrons, and the highest energies demand more than raw scale and dramatic imagery. They demand long confinement and high rigidity control, meaning the particle must be guided and turned around despite its stubborn momentum. Jet turbulence and geometry can limit both, especially if the field becomes too tangled or too intermittent. A jet can be large, yet still leak its most valuable particles. There is also the problem of composition and survival, which becomes acute close to the core where the light is harsh. If the accelerated particle is a nucleus, photon fields near the accretion region can photodisintegrate it, breaking it into lighter fragments. Even for protons, intense radiation fields impose losses, and those losses can dominate before the particle reaches the desired energy. The core is powerful, but it is also crowded with hazards. Synchrotron emission in strong fields drains energy, and it does so faster for lighter particles at the same rigidity. Photopion production can occur in bright environments, turning proton energy into secondary particles and high-energy photons. The AGN can be powerful enough to accelerate, yet also bright enough to destroy the very particles it tries to launch. It is a paradox written in photons. To rescue AGN, theorists add advanced plasma steps, refining the story without changing its basic direction or its physical honesty. The idea is not only shock bouncing, but a two-step boost that pre-accelerates and then finishes. In this view, the jet is not a single accelerator but a chain of accelerators, each handing the particle to the next. The Zevatron becomes a sequence, not a point. One proposed ingredient is Langmuir wave excitation, a classic plasma phenomenon with extreme consequences in astrophysical settings. Strong beams and gradients can drive oscillations in the electron density, producing longitudinal electric fields that store energy coherently. In a visual sense, the plasma becomes a vibrating medium, with electric fields pulsing like invisible drums. The energy is not random turbulence, but organized oscillation. A second ingredient is Landau damping, a mechanism that sounds gentle but can be brutally efficient in the right regime. Waves transfer energy to particles when particle velocities match the wave's phase speed, so a subset of particles can surf the wave and steal its energy. Under the right conditions, this produces rapid heating and energization, without requiring many shock crossings. It is acceleration by resonance, not by repeated collision. In a two-step picture, plasma waves energize particles to a high seed energy, and that seed energy matters because it shortens the climb. Then shocks, shear acceleration, or structured electric fields push the seeds to the extreme tail, where ordinary diffusion would be too slow. The story becomes a relay race, and each handoff must happen before losses intervene. The baton is energy, and the track is hostile. These mechanisms are plausible in principle, but hard to verify observationally, and that uncertainty is part of the tension. They depend on microphysics in regions we cannot resolve, and they must operate in environments that are dynamic and messy. The models also must survive loss constraints, which tighten as soon as one writes down realistic photon densities and magnetic field strengths. The equations look clean, but the source is not. AGN therefore remain prime suspects with a caveat that never goes away, no matter how persuasive the jet looks. They have the raw power and scale, and they are common enough to matter statistically within the local universe. Their fatal flaw is that the same brightness and magnetism that signal power can also sap the particle, like a furnace that melts the tool meant to carry its heat. The Zevatron may exist, yet still fail at delivery. Second suspect is the starburst galaxy, a system where star formation becomes a sustained storm rather than a quiet background process. A starburst is a region where star formation is so intense that supernovae overlap in time and space, turning a galactic core into a layered shock environment. Instead of one remnant expanding into quiet space, many remnants expand into each other's turbulence. The galaxy behaves less like a city and more like a battlefield. Instead of one shock, a starburst offers many, and the interactions are not gentle or isolated. Supernova remnants expand into a shared medium. Their shocks collide and merge, and their combined pressure stirs turbulence on large scales. The result is a volume-filling froth of magnetized gas, threaded with fields that are stretched, folded, and amplified. The magnetic geometry becomes a living thing. The collective effect drives a galactic wind, a large-scale outflow powered by thermal pressure, radiation pressure, and cosmic rays themselves. That wind carries magnetic fields outward and creates termination shocks, where the outflow meets the surrounding halo gas. The entire system becomes a magnetized cauldron, with energy injected continuously rather than in isolated bursts. It is an engine that never quite cools down. On a Hillis plot, starbursts can reach high energies if the wind region is large enough and the magnetic field is sufficiently amplified. Turbulence can amplify magnetic fields through dynamo action, and cosmic ray pressure can modify shocks, potentially increasing acceleration efficiency. In this picture, the galaxy is not a point source, but an extended accelerator with many nested zones. The suspect is not a single object, but a whole environment. Messier 82 is the case study because it is nearby and well observed, and because its core is visibly active across wavelengths. In optical and infrared images, dust lanes cut across a bright central region, while bipolar outflows rise like ghostly chimneys above the disk. In narrowband views, the outflow filaments look like torn fabric, lit from within by shock heating. The galaxy seems to be exhaling. Gamma-ray observations imply an unusually high cosmic ray energy density in its core, suggesting that particle acceleration is not a minor side effect. High gamma-ray flux suggests hadronic interactions in dense gas, which is a crucial diagnostic. Cosmic rays collide with matter and produce pions, and neutral pions decay into gamma rays that escape and reach our instruments. The galaxy glows as a calorimeter, meaning it converts a significant fraction of cosmic ray energy into observable radiation. That calorimeter behavior is a clue about confinement, because it implies cosmic rays are trapped efficiently enough to interact before escaping. If cosmic rays were escaping freely, the gamma-ray glow would be weaker, and the energy would leak into intergalactic space. A starburst can then build a reservoir of energetic particles, a kind of pressure component that participates in driving the wind. The particles are not just passengers, they are part of the weather. The reservoir is attractive for acceleration because it provides seeds, and seeds shorten the climb to ultra-high energies. It also suggests strong turbulence and strong fields, which are the ingredients Fermi processes need to keep particles scattering. Visually, one can imagine a crowded city of shocks, each one a street corner where particles change direction and gain a little speed. The question is whether the city keeps them long enough. But the fatal flaw is again time and escape, and the wind makes the dilemma sharper and more literal. To reach the extreme tail, particles must remain in the system long enough for many cycles, yet winds also advect them out. The same outflow that advertises power can act like a conveyor belt carrying particles away before they finish accelerating. The engine's exhaust becomes its own limitation. If confinement is too good, losses rise through collisions with gas, especially in the dense starburst core where targets are plentiful. If confinement is too weak, particles escape before reaching ZE, and the spectrum cuts off early. The window is narrow, and the window depends on details like turbulence coherence length and the structure of the wind termination region. In practice, the Zevatron may hinge on messy geometry. Starbursts also face an energy budget question that becomes uncomfortable at ZeV scales, even when the total power looks enormous. The total supernova power is large, and the integrated mechanical luminosity can be enormous over millions of years. Yet converting enough of it into a single ZeV particle is demanding, because the tail must be fed without starving the rest of the distribution. The spectrum is a population, and populations have accounting. A starburst can plausibly reach ultra-high energies for heavy nuclei more easily than for protons, and that is a recurring theme. Higher charge helps the Hiller's limit, because rigidity decreases as charge increases at fixed energy, yet heavy nuclei are more deflected in transit, and they are more fragile against background light, so the observational signature becomes harder to interpret. The engine may succeed, while the message becomes blurred. So even if M82 can accelerate, it may not point, and pointing is what astronomers crave when they map the sky. The return address problem returns, because heavy primaries smear arrival directions in galactic and intergalactic magnetic fields. The source could be nearby and still look uncorrelated, like a message delivered after being tumbled through a long magnetized maze. The sky keeps the secret by scrambling the path. Third suspect is the magnetar, a neutron star with an ultra-strong magnetic field far beyond ordinary pulsars. Magnetars are born in supernova explosions, and they compress more mass than the Sun into a city-sized sphere. Their fields can reach 10^14 to 10^15 Gauss, strong enough to distort atomic structure and dominate every charged particle nearby. In artists' renderings, the field lines look like taut cables under impossible tension. Magnetars are tiny on a Hillis plot, but their fields are extreme, and the product of size and field can still be large. The question becomes whether the environment allows escape, because confinement alone is not the same as successful delivery. In a sense, the magnetar is the perfect trap, and traps are not always good accelerators. A particle can be held so tightly that it bleeds energy away. Rotation plus magnetic field generates enormous electromotive force, and the numbers are staggering even by astrophysical standards. Potential drops can reach around 10^18 volts in optimistic models, which is Zev-scale voltage. The magnetar looks like a compact unipolar inductor, a spinning conductor threaded by magnetic flux that naturally generates electric fields. It is an engine you could almost draw with a single diagram. It can in principle strip ions and accelerate them along open field lines, where the particle is not forced into tight closed loops. The acceleration can be direct, not diffusive, and that directness is appealing because it bypasses the long timescales of multi-cycle shock processes. In the most dramatic visualizations, particles are flung outward along magnetic funnels like sparks from a rotating grinder. The motion is fast enough to feel instantaneous, but the escape problem is severe, and it is severe because the fields are so strong and the curvature so unforgiving. Curvature radiation and synchrotron losses can drain energy rapidly, and the power radiated increases steeply with energy and curvature. The particle can radiate away its gain almost as fast as it is accelerated, turning the magnetosphere into a bright break. The Zevatron becomes a lighthouse that taxes its own beam. The magnetosphere is also filled with photons and pairs, and the environment is not empty even when it looks like vacuum. Pair cascades can populate the region with electrons and positrons, and their collective behavior can screen electric fields. Dense radiation fields increase interaction rates, and a nucleus can be photodisintegrated before it leaves the system, especially if it passes through intense X-ray emission. The accelerator is embedded in its own byproducts. Even if a particle reaches high energy, it must get out without being isotropized or absorbed, and the surrounding material matters. The surrounding supernova ejector can be thick early on, and it can act like a wall of matter and radiation. The timing must be right, because the ejector thins with expansion while the magnetar's spin-down reduces available voltage. 2 clocks tick, and they do not cooperate. That timing constraint turns magnetars into transient candidates, which fits their broader astrophysical character and their episodic flaring. The best window may be after the environment thins but before rotation slows, and those 2 clocks run in opposite directions. The window may be short and it may vary dramatically from one birth event to another. A Zevatron might exist only for a moment, so magnetars have a compelling capability and a fatal flaw, and the contrast is sharp enough to feel like a plot twist. They can generate huge voltages and they can in principle accelerate quickly. They may not let the particle keep the energy long enough to escape, and in this game, escape is the final exam. The particle must leave the trap without paying too much rent. Across these suspects, the same pattern repeats, and it repeats with almost narrative cruelty. Hillis confinement is necessary but not sufficient, and mechanism, losses, and escape decide whether the candidate survives. The suspects are not eliminated by one argument, but by the accumulation of constraints that tighten like a net. Each constraint is simple, and together they become oppressive. The Hillis filter also exposes a deeper tension that feels almost like a law of storytelling written into plasma. To confine Zev particles, sources need large size or strong fields, and those requirements rarely come together cleanly. Large size often means weaker fields, while strong fields often mean stronger losses, so the universe seems to offer the ingredients, but not always in the same kitchen. The recipe is always missing one key step. This is why the Zevatron hunt feels like a trap, even to experts who know the equations by heart and can recite the scalings. Each improvement in one requirement worsens another, and each proposed fix introduces a new vulnerability. The universe offers power, but it charges interest, and the interest is paid in radiation, fragmentation, and premature escape. The balance sheet is written in photons and neutrinos. There is also the charge lever, which can make the story look easier at first glance, and then harder on the next page. If the primary is a heavy nucleus, the Hillis limit rises with Z, and ZeV total energy becomes more reachable for a given magnet size. In practical terms, an iron nucleus behaves like a particle with 26 times the charge of a proton, so it bends more easily and stays confined more readily. The same field feels stronger to it, but heavy nuclei bring their own costs, and those costs show up both in propagation and in source environments that are rich in light. They are more deflected by magnetic fields, so source identification becomes harder, and arrival directions can lose their meaning. They also fragment on background light over distance, so the composition we detect may not match what was launched. The messenger can change identity mid-flight. If the primary is a proton, pointing is easier, and propagation is cleaner in some regimes because the charge is minimal. Yet the Hillis requirement is harsher because Z is 1, and the engine must be more extreme to hold and accelerate it. The proton is the simplest messenger, but it is also the hardest to push to the very top. Simplicity becomes a burden. Composition therefore links the engine problem to the astronomy problem, and it does so tightly and uncomfortably. What can accelerate depends on Z, because rigidity controls confinement and acceleration time. What we can trace back also depends on Z, because magnetic deflection controls whether the sky keeps the source's fingerprint. The physics of the source and the physics of the journey are inseparable. The GZK horizon still hangs over every candidate, like a boundary line drawn by the universe itself in the cosmic background light. Even if a distant AGN can accelerate, the particle may not arrive with its original energy, because interactions with background photons sap the highest energies. Nearby sources become favoured by propagation, not because they are stronger, but because they are closer. Distance becomes a form of friction. That pushes attention to the local universe, where the catalogue of extreme objects is limited, and therefore easier to interrogate. It also pushes attention to transient sources, which may not be active when we look, or may have already faded by the time the particle arrives. The hunt becomes a mismatch between what we need and what we see, and that mismatch fuels the mystery. We are searching for engines that may no longer be running. We need nearby, powerful and rare engines, and we need them to operate under just the right microphysical conditions. The sky offers a few candidates, none without problems, and the problems are not cosmetic. They are constraints that come from first principles: geometry, electrodynamics, and interaction cross-sections. In this regime, nature does not allow hand-waving. This is where the narrative stakes rise, because the oh my god event stops being a curiosity and becomes a test of the bottom-up worldview. If bottom-up astrophysics cannot comfortably supply ZeV particles, then the event may be telling us something stranger about the universe's inventory of processes. The discomfort is productive, because it forces the field to sharpen its questions. What else could masquerade as an accelerator? The field does not abandon bottom-up lightly, and it has good reasons not to, because it is anchored in known plasma behaviour. It tests each suspect against Hillis scaling, acceleration time, loss channels, and plausible event rates, and the tests are tightening as data improves. Each new observation, composition hints, anisotropy limits, spectrum features, acts like another constraint line on the detective board. The board gets crowded and the empty space shrinks. Event rates matter because one particle implies a population, and populations imply astrophysical demographics. A Zevatron must not only exist, it must produce enough events within the GZK horizon to match observed flux. Otherwise, the rarest events become too rare, and the mechanism becomes a mathematical possibility without an astrophysical footprint. A perfect engine that never runs is not an explanation. That rate constraint is often the quiet killer, because it's easy to ignore when focusing on maximum energy alone. A mechanism might reach ZeV in principle, yet occur too rarely, or require fine-tuned conditions that seldom align. The universe may be able to do it, but the universe may choose not to do it often enough for us to see. Capability is not the same as contribution, so the suspect list remains short and uneasy, and the unease earned rather than theatrical. AGN offer scale and power, but struggle with losses and hostile environments near the core. Starbursts offer many shocks and strong turbulence, but struggle with escape and energy budgets at the extreme tail. Magnetars offer voltage, but struggle with radiation losses and surrounding opacity, especially early in their lives. Each candidate can be made to work on paper, and each candidate resists when all constraints are applied at once. The story does not end with a clean elimination, but with a growing pressure that pushes the narrative forward. The equations keep pointing toward a corner. The result is not a verdict, but a pressure gradient in the story, and it points toward a different class of ideas. Bottom-up explanations are strained, not eliminated, and that distinction matters. Strain is the space where new hypotheses are born, and where old assumptions are tested hardest. It is where the universe invites us to be less comfortable. If nature cannot accelerate up from ordinary particles, it might instead start high, and that is the top-down possibility. In top-down scenarios, ultra-high energy particles are decay products of something heavier, so the universe does not need a conventional accelerator. The energy is inherited, not earned, and the mechanism becomes one of transformation rather than acceleration. The Zevatron is replaced by a relic. This is the chapter's pivot. The Zevatron hunt shows how hard it is to build a conventional accelerator at the edge of physics, even with black holes, starbursts and magnetars on the table. The next chapter asks what happens if the accelerator is not needed, and if the highest energies come from relics rather than engines. The question stays, but the logic turns. The central question stays the same, but the tone shifts, and the shift is deliberate and a little ominous. Are we hunting engines in galaxies or relics from the early universe, left behind like fossils in the cosmic background? The oh my god particle keeps forcing the question, because its energy sits right where conventional explanations begin to creak. It is a data point that behaves like a dare. For now, the suspect filter remains on the board, and it remains useful even without a final answer. Hillis tells us who can confine, Fermi tells us who can plausibly accelerate, and losses and escape tell us who can actually deliver. The uneasy conclusion is clear, and it is spoken softly because it is not yet a proof. The universe has not shown its hand. Even the best bottom-up suspects strain under energy budget, confinement time and escape constraints, and the strain is not a failure of imagination. It is a sign that the universe is using either rare circumstances or unfamiliar pathways, or both. The mystery deepens, and the door opens to the exotic, because the data keeps knocking, and the next knock may be even louder. The oh my god particle hangs in the record like a dare, a single track etched into desert air and detector memory. It arrived with trans-GZK energy so high that the usual cosmic bookkeeping says it should not have survived the trip. In the reconstruction plots, its energy sits above the smooth curve like a pinprick of defiance, and the detectors remember it as timing flashes across a wide grid. Yet its sky position offered no obvious nearby engine, no bright beacon within the expected horizon, and that absence is part of the mystery. In Chapter 5, we chased Zevatrons through jets, winds and magnetospheres, following every plausible route to 10 Jupiter electron volts. We leaned on the Hillis argument, that simple but ruthless diagram where size and magnetic field draw a boundary line across the cosmos. The suspects could sometimes reach the numbers on paper, especially with optimistic magnetic fields and generous sizes. But the full accounting stayed brutal, because confinement, radiative losses, escape probabilities, and event rates rarely aligned inside the GZK horizon. Even when one constraint relaxed, another tightened, like a lock that clicks shut from multiple directions. Part of the difficulty is that acceleration is not just about reaching a peak energy, it is about keeping that energy long enough to escape. In shock acceleration, the particle must cross a turbulent boundary many times, and each crossing is a gamble against leakage. In unipolar induction, the voltage can be enormous, but curvature radiation and pair cascades can short out the potential. In dense radiation fields, inverse Compton, scattering and photohadronic interactions drain energy before the particle ever leaves the source. The universe offers many ways to accelerate, but it also offers many ways to bleed. So the narrative takes a turn that physics allows, even if it feels unsettling in its implications. When bottom-up acceleration strains, some models start with energy already stored. The particle is not pushed up a ladder step by step inside a cosmic machine. It falls out of something heavier, as if the universe were cracking open an ancient vault. In that framing, the question shifts from engineering to archaeology. What relics could still be buried in the present? This is why exotic theories enter the story at all, and why they persist despite the discomfort they cause. Standard propagation says the universe should shave protons above the GZK threshold over tens of megaparsecs, because the cosmic microwave background is everywhere. That background is not a vague glow, it is a dense sea of photons at 2.7 Kelvin, about 400 per cubic centimetre. For a proton moving close to light speed, those gentle photons are Doppler boosted into a dangerous energy range. Magnetic deflection says charged primaries should not point cleanly back to distant sources, because intergalactic and galactic fields bend their paths. The sky should look smeared, and the spectrum should look suppressed, and in broad strokes it does, until the rarest events refuse to behave. Yet events keep appearing near and above the cutoff, sparse but persistent across experiments and across decades of exposure. Their arrival directions do not neatly cluster on a catalogue of nearby active galaxies or starbursts, at least not in a way that ends the debate. Their flux is low but not zero, and that difference matters because it forces us to explain how any survive. A handful of particles can still overturn a comfortable theory, because the tail of the distribution is where assumptions are tested. If the sources are ordinary, they must be close, powerful, and rare in just the right way, and they must also be active at the right times. The local universe is lumpy, with galaxy groups, filaments, and voids, and that structure should matter if sources trace matter. If the primaries are heavy nuclei, they may survive differently, because photodisintegration replaces photopion loss as the dominant threat. A nucleus can shed nucleons like a ship losing cargo, stepping down in mass while keeping roughly the same Lorentz factor. But heavy nuclei also smear directions more, since rigidity depends on charge, and higher charge means stronger bending. If the primaries are protons, they point better in principle, but the engines struggle harder to reach the top energy without bleeding it away. The tension is not that conventional astrophysics is wrong, because much of it is spectacularly successful at lower energies. The tension is that the highest energy tail forces multiple constraints to be satisfied simultaneously, and it does so with almost no statistical mercy. The Hillis condition demands size and magnetic field, while acceleration time must beat lost time, and escape must not empty the source too quickly. Even the surrounding environment matters, because dense photon fields turn into a fog of interaction targets. When the list of viable engines shrinks, the door to top-down ideas opens wider, quietly at first, then with a kind of inevitability. Top-down is a different kind of origin story, and it reverses the usual intuition about cosmic rays. The universe does not accelerate a particle to 10 to 20 Earth through repeated magnetic kicks. It releases a particle that already carries that energy as inheritance, like a fragment from a much larger mass scale. In this view, the sky is not only a map of accelerators, it is a screen where ancient physics occasionally flickers. The particle becomes a message from symmetry breaking, not merely from astrophysical violence. In these models, the primary energy is a fossil from the early universe, preserved through expansion and cooling. It is stored in ultramassive relics, topological defects, or metastable particles left over from phase transitions, when forces and fields reorganized. Those transitions are not metaphors, they are changes in the vacuum state of quantum fields as the universe cooled. The sky becomes a decay detector, not only an accelerator map, and the relevant question becomes how often the universe drops one of these relic sparks. The rarity is not an inconvenience, it is the point, because the observed flux is tiny. The appeal is simple and dangerous, because it promises to bypass the hardest engineering problem in astrophysics. A single decay can produce a shower of ultra-high energy secondaries without any magnetic bottle, without any long acceleration time, and without any need for a nearby source. The hard part becomes explaining why relics still exist, why they have not already decayed away, and why their decay rate matches the observed trickle. That requires a balance between abundance and lifetime that feels almost tuned, and nature does not grant that lightly. A model that makes the right energy but the wrong frequency is still wrong. One classic top-down suspect is the cosmic string, a concept that grew out of the mathematics of symmetry breaking. Tom Kibble's work on phase transitions suggested that early universe cooling could leave defects, like cracks frozen into space-time, when a field chooses different orientations in different regions. In field theory language, the vacuum settles into a lowest energy state, but it does not coordinate its choice across causally disconnected patches. Where those choices meet, mismatches can become stable structures, and stability is what makes them interesting. The idea echoes condensed matter, where cooling can trap defects in crystals, except here the crystal is the vacuum itself. A cosmic string is not a string of matter in the ordinary sense, and the name can mislead the imagination. It is a line-like concentration of energy in a field configuration, with tension set by the symmetry-breaking scale, and that tension is enormous by everyday standards. In many models, the string's mass per unit length is so high that a kilometre of it would outweigh mountains, even though it could be thinner than an atom. Visually, it is less like rope and more like a fault line in a field, a place where the field cannot smoothly relax. Its gravitational effects can be subtle at a distance, but close up it would warp trajectories and lens light, leaving characteristic signatures. Strings evolve as the universe expands, and their evolution is not static decoration in a cosmology textbook. They stretch with the Hubble flow, they oscillate under their own tension, and they intersect as the network moves. When segments cross, they can reconnect, exchanging partners and cutting off loops, a process called intercommutation. The result is a population of loops of many sizes, constantly forming and shrinking like a cosmic tangle trying to simplify itself. In simulations, the network tends toward a scaling behavior, where the overall pattern keeps a similar shape as the universe grows. That reconnection is not just geometry, because the local dynamics can become extreme. It can create cusps and kinks, regions where the string briefly moves ultra-relativistically and concentrates energy into a small segment. A cusp is a momentary point where the string doubles back and a tiny portion approaches the speed of light, compressing energy into a burst. A kink is a sharp bend that propagates along the string, like a travelling discontinuity in direction, and it too can radiate. In both cases, the important feature is localization, because localized energy is what can become particles. The loop then radiates energy away, and in many scenarios the dominant channel is gravitational waves, ripples in space-time that carry energy off efficiently. That expectation has become more concrete in the era of gravitational wave astronomy, because stochastic backgrounds can be searched for directly. But some models allow particle emission as well, especially when the string couples to fields that can be excited. In those versions, the string's stored energy can convert into super-heavy quanta, and those quanta become the parents of our cosmic rays. The conversion is not guaranteed, but it is permitted in certain field theory constructions. In particle-producing versions, the quanta then decay into jets of hadrons, photons, and neutrinos, and the process resembles a miniature high-energy collision. The final products include protons and nuclei at energies that look impossible for any astrophysical accelerator, because the energy is not earned, it is released. The cascade is governed by fragmentation, the same general physics that turns quarks and gluons into hadrons in collider events, but scaled to energies far beyond human machines. What we see at Earth is the end of a chain that began with a mass scale near grand unification. In that sense, a single air shower becomes a low-energy shadow of a far more violent birth. The signature is not a single clean proton line, and it is not a tidy mono-energetic feature. It is a fragmentation spectrum rich in pions and therefore rich in gamma rays and neutrinos, because pions decay quickly. Neutral pions feed gamma rays, while charged pions feed muons and neutrinos, and those neutrinos travel almost unimpeded. That composition is a test because it predicts multi-messenger companions, and multi-messenger astronomy is now mature enough to apply pressure. A model that makes too many photons at ultra-high energy can be ruled out by photon fraction limits. A model that makes too many neutrinos can be squeezed by the quietness of neutrino telescopes. Another top-down category is the decay of ultramassive relic particles, sometimes described as super-heavy dark matter or metastable remnants. These could be produced in the early universe through non-thermal mechanisms, such as gravitational production during inflationary reheating, then survive as long-lived components. Their masses can be near grand unification scales, far beyond any collider, and their lifetimes must be fantastically long. In practice, that means their decay is suppressed by symmetries, high-dimensional operators, or tiny couplings, so that only a few decay per cosmic volume per time. The model lives or dies on that suppression, because the universe has had billions of years to empty any unstable reservoir. If such a relic decays today, the energy budget is immediate and almost obscene by particle physics standards. A 10 20 eV cosmic ray is tiny compared with a 10 24 eV parent, and that gap leaves room for many secondaries. The challenge becomes lifetime and abundance, because too many decays would flood the sky with gamma rays and distort the diffuse backgrounds we measure with precision. electromagnetic cascades do not keep their initial energy. They redistribute it through pair production and inverse Compton scattering until it lands where our telescopes are sensitive. The universe is not quiet at high energy, but it is constrained, and those constraints are unforgiving. Top-down models therefore live under observational pressure from diffuse backgrounds, and this pressure is not abstract. Gamma-ray telescopes constrain how much electromagnetic energy can be injected into intergalactic space because cascades downscatter into the GeV to TeV range. The extragalactic gamma-ray background measured by instruments like Fermi becomes a kind of calorimeter for all invisible high-energy processes. Neutrino observatories constrain how many ultra-high energy neutrinos can accompany the hadronic channel, because neutrinos are the unavoidable byproduct of pion decay. Even non-detections become powerful, because they carve away parameter space. The sky, in effect, keeps the ledger. This is the key point for the documentary's central question, and it keeps the narrative honest. Exotic origins are not chosen for style, and they are not a refuge for imagination when astrophysics gets hard. They are invoked because the data forces a choice between rare nearby engines, unusual composition, or new physics in propagation. The sky's not asking what we prefer, it is asking what we can defend. And defense requires predictions that survive contact with multiple instruments, not just one dramatic event. And then there is an even stranger possibility, one that feels like stepping onto thin ice. The GZK limit itself might not be fixed if the underlying symmetries of spacetime are slightly broken at extreme energy. The idea is not that relativity fails in daily life, because it clearly does not. The idea is that at the highest energies, the rules might acquire tiny corrections that only cosmic rays can reveal. It is a radical proposal precisely because it targets a foundation, not an astrophysical detail. Lorentz invariance is a cornerstone of modern physics, and it is woven into both special relativity and quantum field theory. It says the laws of physics are the same for all inertial observers, and it locks in the relationship between energy, momentum, and speed. Most experiments confirm it with astonishing precision, from particle accelerators to atomic clocks to astrophysical observations. That precision is exactly what makes the question interesting, because any deviation must be subtle and well hidden. If there is a crack, it must be hairline. But some quantum gravity ideas suggest Lorentz symmetry could be approximate, emerging at low energy the way fluid behavior emerges from molecules. Tiny corrections could appear near the Planck scale, suppressed at low energies, but amplified when energies become enormous. Ultra-high energy cosmic rays are one of the few places nature offers that lever arm, because a 1020 eV proton is still far below the Planck energy, yet it can probe thresholds sensitively. A small change in kinematics can have a large change in what reactions are allowed. Thresholds are like gates, and gates are sensitive to small shifts in hinges. The GZK suppression depends on kinematics, and the mechanism is conceptually simple, even if the details are not. A proton above about 5 ciscamus 10 or 19 eV sees the cosmic microwave background photons blue shifted in its frame, turning millimeter wave light into something far more energetic. When the center of mass energy crosses a threshold, photopion production becomes allowed, and the proton can lose a large fraction of its energy in one interaction. The typical channel runs through the delta resonance, a short-lived excited state that decays and sheds energy into pions. That threshold is a bookkeeping result of energy and momentum conservation, and it is therefore sensitive to how those quantities relate. If Lorentz invariance is modified, the threshold can shift, and the shift can be upward or downward depending on the sign of the correction. The energy needed for photopion production could increase, or the reaction could become less efficient, or the phase space could shrink. In extreme cases, the interaction could be effectively turned off over part of the spectrum, leaving protons surprisingly intact. The universe would still be filled with CMB photons, but the proton would no longer see them in the same way. The same sea of light would become, in effect, less sticky. That would change the cosmic ray horizon, and it would change the logic of source identification. A proton that should have been degraded within tens of megaparsecs could travel much farther, potentially crossing hundreds of megaparsecs with less penalty. The arrival of a trans-GZK particle would then be less paradoxical, because the universe would be more transparent than we thought. The same event would stop being a local mystery and become a global one. It would also force us to reinterpret why the spectrum bends where it does, and whether that bend is propagation or source exhaustion. This idea is not a free pass, and the documentary must treat it with the seriousness it demands. Any Lorentz invariance violation must also survive constraints from other particles and other energies, including electrons, photons, and neutrinos. It must not ruin synchrotron emission in known sources, because we observe high-energy electrons radiating in magnetic fields exactly as expected. It must not contradict precision tests in laboratories, where tiny deviations would have already shown up in controlled measurements. The allowed room is narrow, and it gets narrower every year. In practice, the model must thread a needle between cosmic ray anomalies and everything else we know. Yet the documentary's tension is that the highest energy tail is exactly where such effects could hide, because it is where thresholds live. A tiny change in dispersion relations can have a large effect on reaction onsets, which then reshapes the spectrum and the horizon. The same data that maps astrophysical engines can also probe the structure of space-time, and that dual role is what makes the field feel like a crossroads. Are we doing astronomy, or are we doing fundamental physics with the sky as our apparatus? The unsettling answer may be that we are doing both at once, so the story now holds two competing pictures, and neither is easily dismissed. Bottom-up says particles are accelerated in extreme astrophysical machines, then lose energy through standard interactions with background radiation fields. Top-down says energy is released from early universe relics, or the interactions are altered, or both, and the source is not a place so much as a process. The difference is philosophical as well as technical, because it changes what kind of universe we inhabit. Is the highest energy a product of rare environments, or a leftover of primordial history? The next question is visceral, and it pulls the narrative back to Earth with a jolt of human instinct. If a single particle can carry 50 joules, should we fear it? 50 joules is the energy of a fast-thrown baseball, and that comparison is irresistible because it is tangible. But it is also misleading, because biology does not experience energy the way a bat experiences a pitch. What matters is not just energy, but where it goes, how fast it spreads, and how often it repeats. The fastball analogy is useful for scale, but it misleads biologically, and the reason is geometry as much as physics. A baseball spreads its energy through macroscopic contact and sustained force, crushing tissue and transferring momentum over milliseconds. A cosmic ray deposits energy through microscopic interactions, and it does so in a cascade that is mostly thin air. The primary particle is smaller than an atom, and its first collision is with a nucleus high above us. That first collision is more like a collider event than an impact, and it happens where the air is thin and cold. The interaction cross-section of a single primary with human tissue is tiny, and the odds of a direct hit are vanishingly small. The particle almost never hits a person directly, and even if it did, the first interaction would likely occur high in the atmosphere, tens of kilometers up. What reaches the ground is a diluted shower front, a broad disk of secondaries moving at nearly the speed of light. The drama is spread out, and dilution matters. The shower is impressive to instruments because of coincidence, not because of concentrated harm. At ground level, the shower is many particles, but each carries far less energy than the primary, because the energy has been partitioned. The energy is distributed across square kilometers and across nanoseconds, arriving like a brief invisible sheet. The event is intense in physics terms, because detectors can light up in synchrony, but sparse in biological dose. A person standing under it experiences almost nothing, because most secondaries miss any given body. Even when particles pass through, they usually leave only small ionization trails. Radiobiology cares about energy deposition density and track structure, because damage depends on how ionization is concentrated. Heavy ions in therapy create dense ionization tracks that break DNA efficiently, producing complex damage that cells struggle to repair. A typical air shower muon is penetrating, but it deposits energy slowly, like a minimum ionizing particle, leaving a relatively sparse trail. Even when a shower includes hadrons and electrons, the dose to any one organism is usually negligible compared with natural background variations. The atmosphere, in effect, turns a single violent event into a gentle drizzle. Even the word shower can mislead, because it sounds like a drenching, and this is not that. The shower is not a bullet that drills through a body, and it is not a beam that cooks tissue. It is a brief rain of secondaries, mostly missing any given target, and mostly passing through with minimal interaction. The planet has been exposed to cosmic rays for its entire history, and life evolved under that background, adapting to radiation as one more environmental fact. The biosphere is not fragile glass beneath a cosmic firing range, so the immediate risk to humans is essentially zero, and that conclusion is robust. The oh my god particle is extraordinary in energy, not in direct hazard, and the atmosphere is our shield by virtue of its depth. Still, the documentary's title question is not only about danger, because impact can be subtle and cumulative. A phenomenon can be harmless in a single instance, yet significant as a persistent influence on a system. The relevant scale is not the single event, but the long integration of many events. Cosmic rays are a constant source of ionization in the atmosphere, and their fingerprints are measurable in conductivity profiles. They create ions and free electrons that change electrical properties, especially in the upper troposphere and stratosphere where other ionization sources are weaker. That conductivity shapes the global electric circuit between Earth and ionosphere, a planet-scale system driven by thunderstorms and fair weather currents. The circuit is not mystical, it is an electrical reality, and cosmic rays are part of its maintenance. In visual terms, it is a faint current flowing through air that looks empty, but never is. At ultra-high energy, extensive air showers can create dense columns of ionization, narrow in time but extended in altitude. Those columns concede electrical breakdown in storms by providing initial electrons, and that possibility has been studied for decades. The shower is not lightning itself, but it can help the atmosphere cross a threshold, and thresholds are where rare triggers matter. In a charged cloud, the difference between no flash and a flash can be a small perturbation at the right moment. The question is not certainty, it is probability nudged by physics. One mechanism is relativistic runaway electron avalanche, a process that sounds exotic but follows clear physical logic. In strong thunderstorm fields, seed electrons can be accelerated faster than they lose energy to collisions, so they run away to relativistic speeds. Those electrons then knock loose more electrons through ionization, multiplying the population and creating an avalanche. The result can help initiate lightning leaders, and it can also produce bursts of high-energy radiation observed from storms. In some observations, storms even emit terrestrial gamma-ray flashes, a reminder that Earth can briefly behave like a particle accelerator. This links cosmic rays to weather electricity without claiming cosmic rays control storms, and that distinction is crucial. The atmosphere must already be near breakdown, with electric fields poised close to critical values, and most of the work is done by meteorology. The shower provides a trigger in a system poised on a knife edge, and triggers are probabilistic. The question becomes not whether cosmic rays make storms, but whether they slightly modulate when a storm discharges. If the effect exists, it would be subtle, and it would hide inside the chaos of weather. Over longer timescales, cosmic rays contribute to mutation, and here the story shifts from weather to biology. They are not the dominant mutagen compared with chemistry, ultraviolet light, and replication errors, but they provide a persistent background of ionizing tracks. Ionization can break chemical bonds, create reactive radicals, and damage DNA, and cells must constantly repair such damage. Over evolutionary time, small rates can matter, because evolution is a game of statistics played over immense numbers of organisms and generations. The background is steady, and steady influences can shape outcomes without ever being dramatic. The effect is not a simple story of harm, because mutation is also a driver of variation, and variation is raw material for selection. Cosmic rays are therefore part of the planet's long statistical experiment in biology, a quiet source of randomness that never fully turns off. The biosphere lives under a sky that is not only bright and warm, but also energetic in ways we do not see. It raises a question that is both scientific and philosophical. How much of life's history is shaped by rare, invisible events? And if the rarest events are the most energetic, do they matter? Or does their rarity make them irrelevant? At the frontier, the documentary touches a more speculative idea, and it must be framed carefully to avoid turning possibility into claim. Some researchers have asked whether cosmic ray secondaries could bias biological chirality, the preference for left-handed amino acids and right-handed sugars. Life's homochirality is one of the deepest puzzles in origin of life research, because chemistry alone often produces mixtures. If a tiny bias existed early, it might have been amplified by autocatalysis and selection. The intrigue is that physics contains a built-in asymmetry, and biology contains a built-in asymmetry, and the mind wants to connect them. The weak interaction violates parity, and that is not controversial because it is built into the standard model. When pions and kaons decay, the resulting muons can be polarized, carrying a handedness in their spin and decay products, and that polarization is a real asymmetry. In principle, polarized particles interacting with chiral molecules could create tiny asymmetries in reaction rates or destruction rates. The key word is tiny, because the weak force is weak and chemistry is noisy. Any effect would have to survive dilution, competing reactions, and environmental variability. The hypothesis is not that one shower flips life's chemistry, and it is not that a single muon imprints a biological destiny. The hypothesis is that over vast times and many interactions, small parity-violating biases could be amplified by chemistry and selection, especially in environments where feedback exists. It is intriguing because it connects fundamental physics to a biological fact, but it is not settled science. The evidence is suggestive at best, and the mechanisms remain debated. The honest stance is curiosity without overreach. The responsible stance is to treat it as a question, not a conclusion, and to keep the chain of inference visible. The weak force does violate symmetry, and muons do arrive at the surface in enormous numbers over time. Whether that fact connects meaningfully to homochirality remains an open research topic, one that sits at the boundary between disciplines. If the connection exists, it would be subtle, statistical, and contingent, not a dramatic lightning bolt moment. It would be the kind of influence that only becomes visible when you step back across geological time. This returns us to the chapter's theme, and it ties the cosmic to the terrestrial without forcing a grand claim. The oh my god particle is a messenger from extremes, but its message may be about more than sources. It may be about propagation, about symmetries, and about how high-energy physics couples to Earth's environment through cascades and ionization. The same event that challenges astrophysics also invites us to notice the atmosphere as a detector, and the biosphere as a long-term integrator. The planet is not merely a passive target, it is part of the measurement. Exotic origins also change what we should look for in the data, and they change what counts as a decisive clue. Top-down models predict different composition, often more photons and neutrinos at the highest energies, because fragmentation favours pions. Bottom-up models predict correlations with nearby structure, and a composition shaped by source environments, including metallicity and radiation fields. Lorentz violation scenarios predict changes in the spectral shape near the cutoff, because thresholds move and energy losses change. Each story leaves a different fingerprint, and fingerprints are what science can compare. They can also predict altered secondary production, because interaction channels turn on and off differently, and that changes what accompanies the primary. The spectrum becomes a test of fundamental kinematics, not only of astrophysical demographics, and that is a profound shift. A plot of flux versus energy becomes a probe of space-time structure, and the axes start to feel like a laboratory instrument. It raises an uncomfortable question. What if the universe is not only accelerating particles, but also rewriting the rules of their travel? If that is true, the sky is not just a map, it is a code. To discriminate between these pictures, we need observables that are hard to fake, and we need them in combination. We need better composition tagging through Xmax distributions, because the depth of shower maximum encodes mass and interaction physics. We need improved muon measurements, because the muon content of showers has become a sensitive diagnostic, and a known challenge for hadronic models. We need larger exposure to build statistics above the cutoff, because rare events demand patience and area. We also need careful cross-calibration, because the difference between a steep cutoff and a shallow tail can hide inside systematic uncertainty. We also need multi-messenger strategies, because cosmic rays alone can hide their origins behind magnetic bending. Neutrinos and gamma rays can reveal hadronic interactions at the source or during propagation, and they travel straight. If top-down decay dominates, neutrino fluxes and photon fractions should rise in characteristic ways, and those signatures can be sought. If bottom-up sources dominate, neutrinos may still appear, but their energies and angular correlations should differ. The decisive clue may be a pattern across messengers, not a single spectacular detection. Arrival directions still matter, even when deflection blurs them, because patterns can survive statistical smearing. Large-scale anisotropy can reveal whether sources trace local matter distribution, such as the supergalactic plane or nearby galaxy concentrations. Small-scale clustering can reveal whether a few nearby engines dominate the tail, producing repeated hits from similar directions. Even a weak correlation can be meaningful when the energies are extreme because the background is low. The sky may not point like a laser, but it can still whisper through statistics. This is where the documentary's tension peaks, and it should feel like standing before two doors in a dim hallway. Either the universe is hiding a small number of nearby accelerators that barely satisfy known physics, operating in the local cosmic neighborhood, or the particles are born from relics and defects, meaning the early universe still leaks energy into the present, or space-time itself bends the rules at the threshold, and the GZK limit is not the wall we thought it was. In each case, the implication is large, either for astrophysical demographics for cosmological relics, or for fundamental symmetry. The next chapter must turn this tension into a plan, because mystery without method is only atmosphere. Bigger eyes on the sky will not only catch more events, increasing the sample beyond a handful of legends. They will measure composition and correlations well enough to decide which story survives, and they will do it with cross-checks that reduce ambiguity. To discriminate between bottom-up and top-down, and to test whether the GZK limit truly holds, we need more data, better composition tagging, and bigger eyes on the sky. The Oh My God particle is still one track in the desert air, a fleeting cascade that ended before it began in human time. But in this chapter, it becomes a fork in the road, pointing toward either exotic relics or new symmetry tests. The only way forward is more data, and a sharper translation of what the sky is saying, because the universe has already spoken once, and it may speak again. The impasse is simple. Above the cutoff, statistics are sparse, composition is uncertain, and magnetic systematics keep sources ambiguous. Each rare shower is a clue, yet the sky is smeared by fields we cannot fully map. Now the story shifts from mystery to method, because the next detectors target specific unknowns. Auger Prime adds scintillators atop water tanks, stronger muon sensitivity, and radio integration, enabling event-by-event composition tagging between protons and heavy nuclei. In practice, the scintillator favours the electromagnetic cascade, while the water tanks respond strongly to penetrating muons, two shadows of the same air shower. That split matters because a heavy nucleus fragments early, spreads wider, and leaves a different muon footprint than a lone proton. TAX4 quadruples telescope array area, pushing exposure high enough to test the Ursa Major hotspot and hunt anisotropy as Zevatron breadcrumbs. If the hotspot fades with more data, it was noise, but if it sharpens, direction becomes physics. Cross-calibration matters because North and South still disagree on spectrum and energy scale. EarthCare LiDAR offers a shared atmospheric reference to reduce bias, tracking aerosols and thin clouds that quietly reshape fluorescence light. Then orbit changes the game. Poema's twin satellites watch UV fluorescence over millions of square kilometers and scan the limb for upward tau neutrino Cherenkov flashes. From fly's eye mirrors, improvised, ground-bound and patient, to orbit, the hunt measures how far we will go. We began with a single impossible track over Utah and followed it backward through a century of discovery, from Hess's balloon flights to the fluorescent handwriting of air showers. Along the way, we learned that ultra-high-energy cosmic rays are not just fast, they are fragile messages, shaped by magnetic mazes and by the universe's own background light. The GZK limit, the Hillis gate, and the physics of losses do not end the story, they narrow it, until only the most violent engines or the strangest ideas remain standing. That narrowing is why the Oh My God particle still matters, because it forces every chapter to speak to the next, and every measurement to become a test of nature's extremes. It also taught us humility about what we truly see, because the primary particle is erased, and we rebuild its identity from the cascade it leaves behind. When Agasa, Auger, Telescope Array, and newer events like Amaterasu entered the record, the mystery shifted from one outlier to a population, and statistics became as important as theory. Yet the same obstacles kept returning, like refrains, composition uncertainty, atmospheric systematics, and magnetic deflection that turns direction into a riddle. So the hunt has become a new kind of astronomy, built from cross-calibration, shared sky monitoring, and instruments designed to separate light from muons, protons from nuclei, and chance from pattern. In that sense, the real revelation is methodological, because the path to the source is not a straight line in space, it is a chain of inferences we can finally strengthen. And if those inferences converge, They will either point to a nearby Zevatron within the GZK horizon, or they will point to something even more unsettling. The future chapters are already being written in hardware, as Augur Prime tags composition event by event. Tax 4 widens its net for anisotropy, Earthcare steadies the atmosphere as a shared reference, and Poema imagines an orbital view of the entire hunting ground. Each upgrade is a wager that the Oh My God particle was not a fluke, but a clue, and that the universe keeps sending them. We asked what fired that charged bullet at Earth, and how you trace it back when space bends its path and the CMB taxes its energy. The most honest answer, for now, is that the engine is still unnamed, but the message is clear. Either an extreme accelerator exists closer than we expected, or our assumptions about composition, propagation, or high-energy interactions are incomplete. If these particles are mostly protons, the sky should begin to point, and the GZK horizon becomes a map of nearby suspects. If they are mostly heavy nuclei, the universe can hide the trigger more easily, but the shower itself will carry the fingerprints, in muons, in depth of maximum, and in the way nuclei fracture under background light. If neither picture fits, then the Oh My God particle stops being an astrophysical mystery and becomes a physics one, hinting that the rules bend where our laboratories cannot reach. Even the lingering north-south disagreement, and the question of whether the Ursa Major hotspot sharpens or dissolves are not side plots. They are the hinges on which the final identification will swing. In other words, the question is no longer only what hit us, but what does the universe allow, and how do we prove it? And that is the strange comfort of this story, because the particle that seemed to break the sky also built a new way of listening to it. A single event carrying the energy of a fastball inside something smaller than an atom can still change what we build, what we measure, and what we dare to claim, somewhere within a few dozen megaparsecs, or in a corner of theory we have not yet earned. There is an explanation that will make this track feel inevitable in hindsight. Until then, the Oh My God particle remains what it has always been, an arrival, not an answer, a reminder that the universe speaks most clearly at its limits. When the next one comes, and the next after that, the question will not be whether it should exist, but whether we are finally ready to read its return address. If you want to be part of that reading, follow the data as it grows, support open sky surveys and cross-observatory collaboration, and keep asking where the rarest messengers come from. We asked what fired that charged bullet at Earth, and how you trace it back when space bends its path and the CMB taxes its energy. The most honest answer for now is that the engine is still unnamed, but the message is clear. Either an extreme accelerator exists closer than we expected, or our assumptions about composition, propagation, or high-energy interactions are incomplete. And that is the strange comfort of this story, because the particle that seemed to break the sky also built a new way of listening to it. Until then, the Oh My God particle remains what it has always been, an arrival, not an answer, a reminder that the universe speaks most clearly at its limits. If you want to be part of that reading, follow the data as it grows, support open sky surveys and cross-observatory collaboration, and keep asking where the rarest messengers come from.